Okay. And the first one I'm going to tell you about is the chameleon mechanism. Yeah, I think it's better. Yes, now it's a bit larger. So the chameleon mechanism, so again, the whole idea is to make the mass of my scalar field to be environmental dependent, in the sense that when I'm on the solar system or near a pulsar or black hole, the mass becomes so large that the phi force, the range goes to zero. So I don't see my phi force. That's the whole idea. And the way to do it is basically to look at the usual Lagrangian they've been looking up to now. So Einstein-Hilbert action, a standard kinetic term, V of phi is going to be the key property that I'm going to change. It's going to be self-interacting. And we have the matter fields where you have a coupling, again, with a metric, which will have a conformal coupling A of phi to G mu nu. Okay? So my Ricci scalar comes from the G mu nu metric, and my matter fields, they fill the G tilde metric. So the geometry of space-time you can think of is the A phi, so that's the coupling strength to the metric. Okay, so that's the idea. Now, when I write down the equation of motion, so again, just this is very simple principle, I get the Klein-Gordon equation for the field. So it's box phi. That's the first derivative of the self-interacting potential and the coupling to the energy momentum tensor. So when I do, you can do this as an exercise. It's very simple. I have A cubed phi, the derivative of phi, and the trace of the energy momentum tensor on the G tilde metric. But yeah,
why T is not zero?
Sorry?
T, trace of the
No, the trace is not zero. Well, it's zero for radiation, for relativistic particle, but here I'm assuming dark matter, so baryons, the trace of the energy momentum is the energy density, in fact.
The gravity part has a conformal symmetry.
Yes, well, A of phi is a function of phi. I will tell you, I will show you explicitly what it is. But the trace of the energy momentum tensor is going to be rho. So in cosmology, the energy momentum tensor is just rho, p, p, p. Yeah, rho, and the energy density and the pressure is a diagonal, like let's say in the background universe.
Comparison with the Maxwell theory, conformal theory, and the matter is traceless.
No, so maybe we are using a wrong. So maybe what you mean by conformal theory is different from mine. Mine, I call it conformal because my coupling to the metric is only dependent on phi. So I can do a conformal transformation between the Jordan frame and the Einstein frame. That's, so I'm not sure what you mean. But this coupling has nothing to do with my energy momentum. So my energy momentum here, T, it has dark matter, baryons, photons, neutrinos.
It's extra matter from the scalar. Oh, I realized it.
Yes, so probably from the only on the scalar part. Yes, yeah.
So phi is the field between matter and gravity.
Yes, yeah, yeah. Very good. So, oops, sorry. Yeah. So this is basically the Klein-Gordon equation of the field. The students, you can get it from the varying this Lagrangian with respect to the metric end of the field. So this is the usual definition of the energy momentum tensor. And in the physical metric, you have the conservation of the energy momentum tensor. Okay? If you write down this in terms of the Einstein metric, then you get an extra term here, which is basically for the scalar field, as you'll see. Okay? So, but you can write down as well like that. Okay, so these are the scalar field equation of motion. And now, I told you here you will have a mass which will depend on the environment. So let me show you how this works. So again, if you assume a spherical symmetry, so a massive object, you assume a static, so we can neglect the time derivatives. In a flat space, what you get again is in spherical coordinates. That's the equation of motion that we got, that you have seen it before. Now it's a bit more general. So we have rho is the energy density conserved in the Einstein frame with the so-called conformal coupling to matter. Okay, I'm just doing the same exercise. These are the same equations, but now I haven't tell you what V of phi is nor what is A of phi. And that's going to be the question. So up to now, it's just same equations that I used before. And as you can see, my triangular equation, my scalar field, the behavior of my scalar field will depend on a potential, which is the effective potential of my field. Okay? So it's the bare potential, self-interacting potential, the energy density of matter, and the coupling between the scalar field and matter. Okay, so this is the effective potential, and that means that the mass of my scalar field is going to be dependent of this second derivative of my effective potential. Okay, so now let me show you, in order to have this chameleon screening mechanism, what I need to choose A of phi, my conformal coupling, and I need to choose V of phi, my potential. Okay, so my conformal coupling, I will just Taylor expand the conformal function. I will assume that I have a scalar field which lives in the minima of my effective potential. So I can perturb basically my scalar field to a Taylor expansion around the minima. So I can write down my conformal factor is 1 plus phi times G, which is going to be the strength of the coupling, basically. So G now here is like my beta, my alpha. So it's the coupling strength between my scalar field and the matter, because matter, the rho is the energy density of matter, so it couples to A of phi. So it's going to be rho times phi times G. So that's where the coupling between the standard model fields and dark matter with my scalar field. Okay, so I choose A of phi on this form. Okay, it's a linear expansion on phi. And so my effective potential then becomes V of phi times rho times this part here. Okay? I can neglect the other one. So that's my effective value for phi. And what does it mean? It's like, for instance, if I choose a V of phi, which is just 1 over phi, okay, so I just pick up a potential which is the inverse of phi, and I choose, for instance, a mass term is about 10 to the minus 3 electron volt. So that's a mass term which is on the same order of magnitude as the cosmological constant, because remember, we want these modified gravities, this scalar field, to drive the universe acceleration. So it should have a mass scale of around the cosmological constant mass scale, which is about 10 to the minus 3 electron volt. Okay? So choosing m of about 10 to the minus 3 electron volt, the effective potential is just 1 over phi. I have this coupling between matter and my scalar field, which is phi times rho, and the coupling constant. And what it means, I might, let me, oops, no, not height, so, yeah, height, yes, it's here.
I support you.
No? It should be the height, no? It's a bit strange. Yeah. Okay, thank you. Okay, now we see. So the dynamics of my scalar field, the way my scalar field will depend on this effective potential. The effective potential is made of two parts. One is the V of phi part. That's just 1 over phi. That's this 1 over phi. So just this dotted line here. And then you have a linear function here, phi, which you can think, okay, here I wrote the exponential of beta phi, but it's basically a linear function if phi is very small. So just phi. So the effective potential is this solid line, and that's what the scalar field is going to see. And as you can see, when the energy density changes of matter, so when rho is very high, like on Earth, the density is very high, then this value will change to a very high density. If rho goes to 0, then it will change this effective potential. Okay, so the scalar field has an effective potential which now depends on the energy density of the field. Okay, so in the chameleon screening mechanism, the mass of the scalar field is not a constant anymore. So you don't associate a constant mass to the field because the mass is the second derivative of the effective potential, square root, okay? And now my effective potential depends on rho, the matter density, where we live, okay? So when the density is very high, my effective potential is very steep, and that means the second derivative is very large, okay, of the potential. When the density is very low, so rho becomes very low, so this line comes down to here, then the effective potential becomes very wide open, and the second derivative is very low, and that means the mass becomes very small. So if the mass is very small, the Compton wavelength of the field, so the range of the force, becomes very large. So in low densities, where rho is very small, the force has a very long range. So in a void in the universe, the fifth force has a very long range. If you come to a high dense region like the Earth, the fifth force becomes very massive, the scalar field becomes very massive, and the range becomes very, very short. Okay? And that's the key, in fact, to evade those experiments. Because those experiments, remember, they are performed in high dense regions, and what they say is that if I have a strong coupling, then the force should be very short range. So the mass of the field needs to be very small on the places we are performing these experiments, which are laboratories, solar system, neutron stars, black holes, and the density there is very large. So we are fine, because for my chameleon, the mass becomes very large in those densities. Okay? So that's basically a summary slide. So the chameleon screening, the whole idea is that the mass, which means the range of the force, is density dependent on the environment. That's the chameleon screening. So I have my scalar field with a given self-interacting potential. Any 1/phi to a given power, an inverse power law works for the self-interacting potential. I have a coupling to matter, to my matter fields, and this coupling can be linear with a given constant strength, okay? And the whole idea is that the traditional Yukawa correction, which was this one, which is the exponential of the mass, now my mass depends on the environment because my mass comes from the second derivative of the effective potential. So my mass will depend on rho, okay, that's the whole idea. And since my mass now depends on rho, my effective potential depends on rho. Again, when I am in a vacuum, very large scale universe, the density is very low, so my effective potential now is this solid blue line, and my field sits in a minima there, in that volume. But the second derivative is much, much smaller than 1, okay? So the range is very large, the Compton wavelength of the field is very large, so the field is unscreened. It means the scalar field is active, the fifth force is active, and the scalar field is driving the universe acceleration, and it's changing structure formation because the fifth force is active. When I come, for instance, to very dense environments, like the Earth, the density becomes very high, so this part of the effective potential becomes very steep, and the effective potential now, the blue line, as you can see, is extremely steep now. So the second derivative is very large. If the second derivative is very large, the mass is very large. If the mass is very large, the Compton wavelength of the field becomes very short. If the Compton wavelength becomes very short, my field becomes screened. And that's why when I do an experiment on Earth, you know, even using the neutrons bouncing on mirrors and atoms, the range is so short that it doesn't affect the neutrons even there. The range becomes really, really short. Okay? So that's the way the chameleon screening allows us to avoid constraints on the fifth force. The whole idea is that the mass of the field is environmental dependent. It's not a constant. Which is a bit strange, just because we always have this idea that particles have a constant mass, but every time we have in fact couplings, in modified gravity, usually the particle masses change. You know, even the electron mass will change, for instance. in these theories, and there are constraints. We have constraints from BBN, Big Bang nucleosynthesis, that the mass of the particles, of the electron, of the different particles, they cannot change so much, like I think is like maybe 5% or so, from the BBN, or 10%, from BBN up to redshift 0 today, okay? So, but the mass changes, but this theory still satisfies Big Bang nucleosynthesis constraints. I don't have time to go through that, but if you're interested on BBN, Big Bang nucleosynthesis, we can talk about that. So the mass of the field changes with the environment, okay? So that's one way of screening theories of modified gravity, playing with the mass. You remember the other way that I told you is to play with the coupling. Yes, because all these constraints is this degeneracy between the mass and the coupling. Either the mass is very large and the coupling can be large, so the range very small and coupling very large, or the other way around. So the screening mechanism that plays with the coupling, so you have the strength of the fifth force which depends on the local density, it's called the symmetron. Okay? So the symmetron, again, the whole idea is that this coupling between the scalar field and the matter fields, it will become environmental dependent as well. So the choice here now is a phi square potential, like this. It's a phi square coupling. And so what we are going to do is that alpha, the coupling, the Yukawa correction, is not going to be a constant anymore, but this will depend on the local environmental density. So when you write down the Klein-Gordon equation for the scalar field, you see that the scale, I'm not writing it now, I'm just showing you now the effective potential. The effective potential is going to look like this one. So it's a phi square term and a phi to the 4th term. So I'm choosing my V of phi to be a phi to the 4th term. Okay? So choosing the coupling, a phi square, and the V of phi, self-interacting potential, which is a phi to the 4th, I get an effective potential that looks like that, and there's some free function which is mu and m. Okay? So this potential, as you might, if you study the Higgs mechanism, you know, it looks like the potential very similar to the Higgs field, but now instead of the temperature, we have the energy density. So it's a potential that when the energy density is very high, like the Earth, rho is very large, so the term that dominates this effective potential is the phi 2 square term. So the effective potential just looks like a parabola. Yeah? And the scalar field comes to the minima, as usually. We are all lazy, so we always minimize the energy. Okay? And when the scalar field comes to the minima, phi is equal to 0. And when phi is equal to 0, then A, the conformal coupling, is equal to 1. If it is equal to 1, then there is no coupling. So the matter fields, they just fill the usual geometry from the universe. Okay? So if you have an effective force, a fifth force, basically the fifth force disappears because the scalar field decouples completely from the matter fields. Okay? Now in the other situation when rho now is very low, so if you go to the very large scales of the universe, when rho critical is several orders of magnitude lower than in the solar system, what you have is that the other terms of the effective potential become important, the phi squared and phi to the 4th, and we have that the scalar field rolls down to the other minima of the potential. So the scalar field acquires a non-zero vacuum expectation value. Yes? So this is a non-zero vacuum expectation value. So what it means is that on the conformal coupling, A to the phi, then phi is not 0 anymore. We leave a VEV, a vacuum expectation value. And so that means that the scalar field will be coupled to the standard model fields and to the dark matter as well. So the fifth force in low dense regions will become active because the coupling becomes strong there as well. Okay? So that's the idea for the symmetron screening mechanisms, is that the strength of the fifth force depends on the environment. So the range of the force is always the same. It doesn't change. Okay, that is a parameter that we can choose on our theory. By choosing m and mu, we can choose the range of the fifth force, but the strength, the coupling, that will change. So as you come to high dense regions like impulsors, where the density is very high, basically the fifth force is screened away. Yeah, so these are the two main screening mechanisms that I wanted to tell you about. Now, I'm going to show you tests, cosmological tests for scalar tensor theories of gravity. One of them is going to be the symmetron, so I'm going to show you how that works in the Einstein frame. But I want also to show you how things work in modified gravity theories work on the Jordan frame. And for that, I'm going to basically use the f of r gravity example because it's very explicitly on the Jordan frame. And I will show you the symmetron because it's explicit on the Einstein frame. Again, all the observables that we measure, we only measure dimensionless quantities. And dimensionless quantities, they are independent of the frame you work on. If you like to work on the Jordan frame, that's fine. If you like to work on the Einstein frame, it's fine. When you calculate something that we observe, we can measure, measurements is always about comparing things. As I gave the example to one of your colleagues, I said she was 2 meters tall. And what does it mean? She's 2 meters. It means she's twice the size of the meter. So I'm comparing her height with the length of what I call a meter. So it's a ratio always. And that's what, when we do physics and we do measurements, we only can do ratios. So we only get dimensionless quantities, and those are independent of the frame. So it doesn't really matter. But I will show you now a concrete example for an f of r gravity. So an f of r gravity is a gravity where, besides the Ricci scalar that we have, besides Einstein-Hilbert action, we add some function of r. Okay, so this was introduced by Sorobinsky in the 1980s as an inflationary model. So the f of r here was an r squared term. So at very high curvature, so in the early universe, we can drive an acceleration of the universe. That's inflation. That's the r squared for Sorobinsky. But then later, Carroll et al. And other people as well, they introduced the f of r as a possibility to drive the universe acceleration today. So they introduce a 1 over r term. So when the curvature becomes very low, like nowadays, the f of r will drive the universe acceleration there as a 1 over r. So that's the action there. Okay? So we will see that a few ingredients that we will use a lot f of r, but this is the first derivative of the function f with respect to r, and I will tell you later what is function r. And in fact, you will see that this series of f of r, they are equivalent, conformally equivalent to the scalar tensor theories that I've been talking about, like a scalar field coupled to the Mota fields. Okay? And this scalar field equivalent in the f of r theory, basically, the scalar degree of freedom is this first derivative here, df dr. That's the extra degree of freedom that exists in this theory. Okay? You will see that. And the mass of that extra degree of freedom is basically the second derivative. So the second derivative, it's going to be the square of the Compton wavelength of the theory. So it's the inverse of the mass. Okay? You will see that a bit later. Okay, so just to introduce you. Okay, so we need to know what is f and see how this theory is related to how it has a screening mechanism, for instance, yes? Because otherwise this theory is also ruled out by experiments. So let me show you first the equivalence between this theory and the scalar tensor theory. So when you write down the Einstein equations or the modify Einstein equations for this theory, this is what you get. So you recognize here the G mu nu, so the Einstein tensor, the T mu nu, that's the energy momentum tensor. And then you have all these extra terms, which comes from the fact that you have the f of r function there. So you have all these extra terms. So you get a much longer Einstein equation. And this is a good exercise for the students to show that the modified Einstein equations, we are working on the Jordan frame here because it's very explicit. It's basically this long expression here. And you can write it down for any form of f. Yes, I haven't told you what f is. I will choose what my f of r is a bit later. Okay? And what you'll find is that you'll have fourth order equations because you have here derivatives of f with respect to r. You know, you have here fourth order equations. So it can be very dangerous because it can be due to the Orthodowski theorem. You might think there are instabilities in ghosts, etc. But in fact, that's not the case. The Hamiltonian is bounded from below, so we don't have problems in these theories, in fact. And that's kind of an exception. Okay, so let's take the trace of the modified Einstein equations. If you take the trace, what you'll get is this equation. So again, another exercise for you guys to do it in your, if you want. With Maple, that's easy. If you do it by hand, I don't think it's a good exercise to be done tonight. So you can take the trace, and if you assume that we are in a matter-dominated epoch, so we only have matter now, non-relativistic matter, you get the trace that is just rho. The energy density, you have the usual Ricci scalar coming from the trace, and you have these other terms related to the f of r terms. Now, as you can see, this equation already has a box of f of r there. So that's the derivative of f with respect to r, some source term. So this equation here already resembles a Klein-Gordon equation for the scalar fields. Yes, remember, scalar fields like box phi and some effective potential on the other side. So I have a box of a scalar field and some kind of strange terms there, some kind of effective potential. Yes? So in fact, we can see that when this derivative is very small, and when you have f is much smaller and basically at high curvatures, okay, this is very small, so we get an equation which is basically now looks like very much a Klein-Gordon equation. So box of a scalar field, so f of r is a scalar field, is basically equal to the difference between the curvature and the energy density. Okay, the 8 by g. Okay, so my scalar field is in fact sourced by the difference between the curvature and the energy density, which in GR, you think that the curvature basically is related to the amount of matter there is. But here in this f of r gravity, there's a difference between the curvature and that difference is precisely what gives you, what sources your field. And now you can also you can do these calculations in the evening if you want. You can calculate what's the mass of my scalar degree of freedom, this FDR, okay? And basically you see basically the inverse of the double derivative there, okay? So just saying that the f of r gravity looks like a scalar tensor theory because my f of r term basically looks like a scalar field as an equation of motion like the Klein-Gordon equation of motion, where my scalar degree of freedom also has a mass term which is basically proportional to the second derivative there. So just to give you an example of that.
So, sorry, I don't understand why the trace of that equation can be interpreted as a scalar field.
It does not. I'm just saying it looks like, but I will show you, I think on the next slides, that it can be really, this is just like a scalar field. But I'm just showing that it resembles a Klein-Gordon equation. Yes, it's a box of f of r, so this is a scalar. Yeah, it's a scalar with something in there and some other terms. So because the Klein-Gordon equation of a scalar field is box phi with some other terms, the effective potential, yes. This is what I'm trying to say. I'm going to show you now explicitly that that is in fact the case. This is just the f of r gravity. It's just equivalent, conformally equivalent, mathematically equivalent to just normal gravity and the scalar field coupled to matter. I'll show you. I'll show you. Or then you can do the exercises tonight instead of coming for dinner. Yes. Very good. Okay, so let me show you that. So now I just put all the f of r together. Okay, so I just have an action, and I put all the f of r. Now it's not r plus f of r, just do the whole f of r and other fields. In my here, I'm just showing you the steps to show you how this theory of gravity is equivalent to a scalar tensor theory. Okay, so instead of modifying the r part, I'm going to basically to include a coupling to matter fields there. Okay, so this is what I will try to do. I can choose a conformal transformation. I can choose a transformation where instead of having r, f of r, I will have r, a modified one, a scalar field which has a kinetic term and a potential term, and then a coupling to s. And this transformation basically is this one. And that you can do. That's quite easy to be done. You can do it like in 20 minutes. Okay? You can do it tonight. So if you choose a phi, which has this expression here, so it's the log of df dr, or df of r, you can rewrite my action like this one here. Okay? So as you can see, df dr, that's going to be my scalar degree of freedom. That's why I was telling you before that df dr or f of r with the r below is basically the scalar degree of freedom. It's because for doing this conformal transformation, you can come from the Jordan frame, that's the Jordan picture, to the Einstein frame, to the Einstein picture. Okay? Now this field now couples and modifying the standard model fields there. And now I've introduced a kinetic term, but I have to introduce also a self-interacting potential. So what does the potential look like? The potential looks like this one. Okay, so it's a bit complicated. But when you do the conformal transformation, that's what you get. You can have like your self-interacting potential of the scalar field, so that I'm doing f of r, is basically given by this one. Some derivative of r, f of r, some derivative divided, etc. Okay? So if you apply this transformation, you go from an f of r theory to a theory which has just general relativity plus a scalar field with couples to matter, and the coupling strength is 1/3. It's a constant coupling, just 1/3 there. Okay? The coupling to there. So f of r gravity is a conformally equivalent to scalar tensor theory, and now you understand also why we also don't have instability. So that's another way, because in the Einstein frame you don't see these instabilities because there's no higher order derivatives on the equations of motion. The equations of motions, they are all second order in the Einstein frame. So the f of r theory I'm going to work on is a very specific one. It's an f of r theory which has embedded the chameleon mechanism. Yeah, because if it didn't have any screening mechanism, the f of r gravity would be ruled out by the pulsar, by the neutrons bouncing on a mirror, by the Cassini probe. It would be ruled out. So in order for these f of r gravities to be valid, they need to have a screening mechanism. And if I choose my f of r function like this, okay, I get a chameleon screening mechanism in there. So this function, if I'm in a low density region, I have a strong deviation from GR, so my f of r is alive and kicking with a strong force, okay, with a very small mass, so a very long range equational motion, so my scalar field will have a very long range, my free force. And if I come to the high dense regions, my f of r basically will disappear, okay? And I will show you now a bit explicitly how it works. But you can see, so I'm going to choose now, now we have some three parameters. Yes, you have n, you have m, you have c1, c2, so these three parameters can be chosen in order to satisfy present day's constraints. So most of the time I will work with n equal to 1, and C1 and C2 and M I'm going to choose in order to drive the universe acceleration. Okay. just to summarize, so I'm going to tell you about cosmological tests, very specific two theories. They are modified theories. One is the F of R gravity, which has embedded a chameleon mechanism, so the mass changes with the environment. The other one is a symmetron scalar tensor theory, where it's the coupling that depends on the environment. Okay? All right, so in order to do cosmological tests, usually we have to do perturbation theory in cosmology. Okay? Of course, you can start by looking at the background universe. So you assume that universe is homogeneous and isotropic, and you just look at constraints, from type 1a supernovae, just to see if our model fits the supernovae data. We can do that. We can also look at, the distance to the baryon acoustic oscillations. That's also a background universe constraint. I want to do a bit more complicated than that, because those experiments, those kind of tests, they put constraints on this series, but they will be very easily evaded. Okay, so I want to show you constraints for the fifth force, where you have clustering of matter. So the clustering of galaxies, properties of clusters of galaxies, they will change. That's what I want to tell you about. And for that, I need to do cosmological perturbation theory. So I need to perturb my background universe from the pure Friedmann-Robinson-Walker metric to a perturbed metric. Okay? So I'll just give you very general cosmological perturbation theory. I hope you know that already a little bit. A little bit, yeah. Okay. All right, so usually what you do then, you start with your metric, your space-time, and you perturb the metric with the two Bardeen potentials, so they are two scalar fields. You can, of course, perturb the metric, the vector perturbations and the tensor perturbations, but we'll focus only on the scalar perturbations, okay? And they can be decoupled in the linear regime anyway. So you perturb your metric, so instead of the Friedmann-Robinson-Walker background, you have these two Bardeen potential, psi and phi. We are perturbing also the matter density in the universe. So rho is going to be equal to the average density of matter, rho bar, plus the perturbation delta. Okay? And you will have also some velocity. So the divergence of the velocity, we call it theta. Okay? So you plug this into the Einstein equations. Okay? And even before that, you can plug it on the conservation of the energy momentum tensor, okay, the Bianchi identity, and you can get the energy momentum conservation basically, okay? So delta dot is just minus theta plus 3 phi, okay? So from the energy momentum conservation, and then you will also have the perturbed Einstein equations, delta G mu nu, delta T mu nu, okay? Which from there you can get basically two equations. Well, you get a couple, but they're two very important equations. One is the Newton-Poisson equation. Now you see why they call it Newton-Poisson. We are in GR, yeah, general relativity, where basically we say that the curvature space is sourced by matter, okay, and then some A is the scale factor. The perturbations in matter, there's also the velocity perturbations, and the K is the wave number. And we also have a very important equation for general relativity where psi minus phi minus psi is equal to 0. So there is no gravitational split if you're considering only the matter epoch. And that means that phi is equal to psi. Okay? And that's the key feature of general relativity. That's what will make you the Poisson potential to be just equal to the Newtonian potential, okay? And this is in the Newtonian gauge. So psi and phi, they are just the same in general relativity, okay? So I hope you had seen this before, but that's the idea. Now, in F of R gravity, we also have a modified Einstein equations, okay? So now instead of just R, we have the F of R, and we do the same. We perturb the Einstein equations, this is what we get. So we have an equation for psi, which is proportional to rho, but also proportional to the perturbations in my scalar degree of freedom, delta F of R. So that means that my potentials now of the metric, they are sourced by the matter. If I have a lot of matter, I will perturb a lot my space-time, but they're also perturbed by my scalar field there, the scalar degree of freedom. Okay? And since I have my scalar degree of freedom, I have also the corresponding to the Klein-Gordon equation for my scalar degree of freedom, for my f of r theory, delta of f of r, which is equal to these parts here. Okay? And the most important equation is the equation here, psi plus phi, which now is not equal to 0, but is going to be equal to the perturbations on the scalar degree of freedom. Okay? So remember that f of r is just df dr, and that's the propagating scalar degree of freedom. So that's what you can think of, if you prefer to think on the Einstein frame, that's what you can think as your scalar field, okay, if you prefer to think on the Einstein frame. So that's your propagated scalar degree of freedom. And the important part here is that the gravitational split, so psi is not equal to phi anymore, but it's proportional to the scalar degree of freedom. And that's when the Poisson potential is going to be different from the Newtonian potential. It's going to come from there because the gravitational split is not 0 any longer. And we'll see the details a bit later. Okay? Okay, now in order to solve these equations, we need now to choose what is our f of r. Yes? Otherwise, we cannot choose. And as I told you, I'm going to work with a potential for the f of r of this form. It's a very strange form. Okay, it's not an r squared term. That would be very nice from Starobinsky. That is a term r squared leads to inflation. So if I want dark energy, I need some kind of 1 over r term to dominate nowadays when the curvature is very low, so it drives the universe acceleration. But since a 1 over r term is ruled out by local experiments, solar system experiments, because it has no screening mechanism, the 1 over r f of r gravity. So I need to have a more complicated term. So in order to have a chameleon screening mechanism, I need to have this kind of form. You have to cook it up. Okay? So this model is called the Wu-Savicki model. It's a very specific model for f of r, which is a viable one. So it passes the solar system constraints and all the pulsar constraints, etc. So in this model in general, f of r goes to 0 when r goes to 0. So in the future, when the curvature of the universe goes to 0, this f of r will go to 0. So there's no cosmological constant in there. So it's going to be different from lambda CDM. Because in the lambda CDM, as the curvature goes to 0, the whole universe will be dominated by a cosmological constant, not in this model. Okay? So that's the difference from the lambda CDM model in the very near future. Now, we want this model to behave like lambda CDM in the sense we want this model to drive the universe acceleration. So we need somehow to be sure that we have a cosmological constant somehow in this f of r term. So in the high curvature, not really high, it's like nowadays curvature of the universe, okay, but when r is larger than m, my f of r, I wanted to write like, this is also an exercise for the after class. If you don't want to come for dinner. So if you do r much larger than m, you can Taylor expand this function. And trust me, so if you Taylor expand this function, you get it like a constant plus m squared over r to a power of n. Okay? So we can choose lambda. So lambda is basically by C1 divided by C2 over m. Okay, so that's just Taylor expanding that form. Trust me, you get it there. So it's a constant plus a 1 over r term. That's what you get. Okay? And we want this f of r to drive the universe acceleration today. So we want to include some kind of energy density of the universe today. So we just say that m is basically h naught squared, the amount of dark matter that we have today, and C1 over C2 is basically the ratio of the observed cosmological constant today over the omega matter today. Okay? So if you do that, basically you can get this f of r model, which looks very strange, to have a chameleon mechanism, so it's not ruled out by local gravity experiments, and at the background level, basically to behave as a model where there is a cosmological constant today that drives the universe acceleration. Okay? So it's a viable model for cosmology. Okay, and of course you can write. Let's see what's the time. Yeah. And of course, you can write down, now that you know what are the parameters, you know what is the scalar field. So the scalar field is going to be 1 over r, and there is these terms in there. Okay, I don't think you really need to know all these expressions, but basically what I'm trying to say, you have r plus f of r. The first thing you want to have is a chameleon mechanism in that, so it's not ruled out. So you choose this very strange formula for the f of r. So you are sure that it passes all the gravity experiments. And then the second one, you want this f of r theory to drive the universal acceleration today. So you need somehow to have some constants there that are tuned to be the cosmological constant nowadays. That's the dark energy, amount of energy that we have. And so we have to tune these constants to get the dark energy there. And if you have that, basically you have a background which is going to be very similar to dark energy, to a lambda CDM, and this is what I'm going to show you. Okay? So let's look at the background cosmology first. So when you calculate the Friedmann equations, okay, hopefully those ones, all the students have seen them, okay? You have the modified Friedmann equations, so it's the Einstein equations where you assume that the metric is Friedmann-Robinson-Walker, okay? So there's no Bardeen potential, there's no perturbations there. So you have a modified Friedmann equation. So we have h squared 8 pi g over 3 rho, that's the usual Friedmann equations in general relativity, but now you have the f of r, so we have some extra terms on the Friedmann equation that they look like that. Okay? It doesn't matter. And what you have is that if you calculate what's the effective, equational state for my universe, it's going to be proportional to this y term, which I basically make it proportional to h squared minus 8 pi g over rho critical. So h squared minus that term, so I call it y. Okay, so it's basically, I put all these terms, f of r terms, on one side of the equation, and 8 pi g over rho on the other side of the equation. So that's the difference. That's what I call y. And my universe equation of state, the effective one, is just a ratio between the derivative with respect to the scale factor over y, okay? Just trust me, okay? You can get that. So if I do a plot of the equation of state as a function of redshift, okay? So now I want to know, for my f of r theory of gravity, what's the effective equation of state of the universe, okay? So effective equation of state as a function of redshift. So lambda CDM, the equation of state is always minus 1, yeah? That's the equation of state for the cosmological constant, minus 1. For my f of r gravity, the equation of state will depend on my function y. And my function y basically is all these expressions which depend on FRR, FR, and F. Okay? So my equation of state for my f of r dark energy, let's call it, depends on the value of f of r. So if the scalar degree of freedom is equal to 0.1, my equation of state today is minus 0. I don't know. What is that? 8 or whatever. Okay? If I decrease my scalar degree of freedom value today to 0.03 or 0.01, I'm start to approach the lambda CDM value, minus 1. Okay? So if my f of r, which is the value of my scalar degree of freedom, remember this is just a scalar field. If it's very small today, I'm just approaching minus 1. So my model at the background level for very small values of f of r basically is lambda CDM. Okay? And in fact, in order to pass gravity experiments on Earth in laboratories and solar system, in order to pass, even with the chameleon mechanism, I need to have an f of r which usually is about 10 to the minus 5, 10 to the minus 4, 10 to the minus 6, or below. So the value of my f of r today, the value of my scalar degree of freedom today needs to be very small. So this f of r gravities usually, they have a background which is very similar to lambda CDM. Okay? So the equation of state, but it drives universal acceleration, and it's a modified theory of gravity. So if you look at the supernovae data, it's not a good probe of this series of F of R gravity because they're very similar to lambda CDM, just because they need to pass the gravity experiments. So the question that I want to keep in your mind is, okay, so how can I test these theories? If they look like lambda CDM, they are too perfect to be good. You do not want to come up with a new theory of gravity, make our life complicated, have a strange F of R theory, to basically get the same value as a lambda CDM. Yeah, that's too much work. Let's make our life simple, just a cosmological course, and that's it. Okay? So my aim is to make your life complicated with a complicated theory, but let's try to find some signatures. And hopefully in cosmology, I will show you there are some very strong signatures on this theory. But they're not at the background level. We need to go to perturbation theory, and we need to do structure formation. Yeah, maybe I still have a few minutes. No, it's... Yes, okay, yeah. Okay, very good. So let's do a bit of structure formation. So again, structure formation in general relativity, you just have the perturbed metric with two Bardeen potentials. You perturb the equation, so you get some kind of Poisson type equation. You have a perturbation on the curvature. So if you have F of R gravity, you add some extra terms to these equations. Yes? So one, you source now the curvature. The curvature is not only sourced by the matter in there, but also there is a scalar field living there. And the scalar field also has perturbations, so the scalar field perturbations also source the curvature in my space-time, in my curvature. And also, the Poisson potential is not only sourced by the energy density of dark matter, or baryons, but is also sourced by perturbations coming from R, and in fact from the F of R part in there as well. Okay, so what is important is that curvature is sourced by the F of R, and the Poisson potential is sourced by some kind of effective energy density. It's an energy density which is the matter plus something that comes from the fact that I have this F of R gravity or my scalar degree of freedom there. Okay, so that's how I modify structure formation, because my curvature will change, my Poisson potential changes, that means matter in the universe will feel the fifth force, basically. And that's why we'll cluster in a different way. So let's start first with linear and very large scales. Okay, so we're now in the linear regime of structure formation. And in my other lectures, I will show you the non-linear regime. So in the linear scales, we have linear perturbations. So it means the curvature perturbations, they are linear, they are quite small. So it's a perturbation to the F of R metric. Okay. I'm going to assume as well, just to show you some analytical results, quasi-static approximation. So I'm going to neglect temporal variations on the field, just to show you some of the results. Okay, to solve the equations analytically a little bit. Okay, so I'm just assuming quasi-static approximation. So my scalar field perturbations will be very small. So basically, I only keep the spatial gradients, yes? But you remember the spatial gradients? That gives you the phi force, classically. So the phi force is going to be there at linear scales. I have to also set up some model parameters. So n, you remember my F of R, there was an n there. I'm going to keep n equal to 1. And this mu parameter, I'm going to use it to simplify a little bit my equations, is basically tells me what is the value of my scalar degree of freedom at the background level today, divided by 10 to the minus 6. In some very strange unit for you, if you are theoretical physicists, you're not used to these units, but this is megaparsec. Okay? So megaparsec for you, usually you do theoretical physics, you don't know, that's usually the scale of a galaxy cluster. Okay? So solar system is the astronomical unit. Yeah, that's an astronomical unit, the distance between the Earth and the Sun. Astronomical unit, so when we talk about planets, etc., solar systems. If you go to galaxies, you start to talk about parsecs, to kiloparsec scales. Okay? If you go to clusters of galaxies, you go to megaparsec scales. If you go to, the observable universe, you start to talk about gigaparsec scales. Okay? So this series of modified gravity, the symmetron, the chameleon, and even the Galilean, the massive gravity ones, although the massive gravity is a bit different. Usually, these fifth force, the ranges are about megaparsec scales. So the range of the fifth force is about megaparsec scales. So the Compton wavelength is the inverse of that. So these are ranges which fifth force that act in galaxy clusters, scales, and below, in fact. Okay? And that's why my F of R, when my F of R gravity is about 10 to the minus 6, when the vol is about 10 to the minus 6, so it's very close to lambda CDM. Remember that my F of R, if it's very small, becomes almost lambda CDM. When it's about 10 to the minus 6, the range of my fifth force, and that's the range basically, is about 3 megaparsec. So that's galaxy cluster scales. I'm on the megaparsec scales. Okay? Just to give you an example why. So that's a nice parameter for people who do structure formation. Maybe you're a theoretician, so you don't care, but for astronomers, it's important. Okay? Very good. So when you write down the Klein-Gordon equation for my scalar degree of freedom, so the equation for my F of R, basically I have a mu, so perturbations in R, and matter also sources my scalar degree of freedom. Yeah, that's what this equation tells us. That matter sources my scalar degree of freedom, and I have also perturbations here with R, with some very confusing terms. It doesn't matter. Okay? So I just say that the gradient of my scalar field is sourced by matter. Remember that I calculated when I wanted to show what's the fifth force for my scalar field, I had to calculate the gradient of the profile of the scalar field for a spherical massive object. Yes, one massive object, and I calculated the gradient of the profile of the scalar field, and the force was the gradient of that. Now I don't have one object. What I have is a distribution of matter in my universe, but I still need to calculate what's the gradient of the scalar field in my universe. So that's the equation basically that I need to solve. Okay, so it's sourced by matter distribution and also a little bit by my own scalar fields. If I go to the Fourier space to solve these differential equations, so instead of having spatial derivatives, I go to K, that's the momentum, yeah, K, one of the wavelength, okay, so this is just a Fourier transformation of the equations for the Newtonian, Poisson-Newtonian equation. What I get is an expression like this. So my Poisson equation is sourced by matter, but there's also a term here, this mu, which is proportional to the value of my scalar field today. There's K, so there's a scale dependence because there's a mass associated to it, okay? So we have for my Newtonian potential, we have this, and that means that now I can look of how gravity makes matter cluster. That's the equation that tells me, okay, how gravity makes matter cluster. And I can look in this in two solutions. One, I can look at the very large scales. So K goes to 0, very large scales. K is one of the lambda, the length scale. So K goes to 0, very large scale. So I have K squared psi. When K goes to 0, this is equal to 4 pi G rho m delta m. That's the very large scales. That's the equation. And when I come to very small scales, I have it 16 pi G rho m over 3. So I have a different one. Small scales, that K becomes very large. So you can neglect these other terms. Okay, so it becomes 4 over 3. So 4 times 4 is 16, and the 3 survives. Very large scale, K becomes very large. So these terms become very large. So this is equal to 1. Okay, that's why. So for those of you who know structure formation in general relativity, you will notice that this is just pure general relativity Poisson equation, okay? While this one is a modified Poisson equation for general relativity. So what it means that if you are an observer at small scales, okay, then you have a very strong gravity force. So matter fields at small scales, matter fields 4 over 3 times more gravity than if you are at very, very large scales. So at very large scales you have general relativity, while at small scales you have the scalar tensor theory. So you have a modify gravity. So you have a fifth force. Okay, this is what it's telling you. So very large scales is just general relativity. At small scales, you have the fifth force. So what it means, yeah. Sorry, how small? So yeah, so this is just perturbation theory. So it's not exact, but very good question. That's what I was going to say. So this scale basically is the range of the fifth force. So if the fifth force is about 3 megaparsec, if you choose this kind of model, 10 to the minus 6, then this scale is going to be around 3 megaparsec or 10 megaparsec, like on the megaparsec scale. If you go for a 10 to the minus 5, 10 to the minus 4 value there, then the range becomes larger. You can go to dozens of megaparsec, hundreds of megaparsec. So the range where the fifth force becomes active, it's the range of the fifth force. Yeah? So if the fifth force is the length of my arm, only this region around me are affected by my strong extra gravity. If my arm becomes very long, then there's more range, more matter which will be affected by me. So it's around, you will see, you can choose the parameters, of course. If you have f of r gravities and chameleon z's modified gravities, if you have more than 30 megaparsecs, 20 megaparsecs, they are ruled out. So usually we say around 1 megaparsec, 2 megaparsec, and you will see that even that is, on the last lecture I will say that maybe they are even ruled out, maybe, those ones. So I would say around 1 megaparsec, well, order of magnitude, you can go to 10 megaparsec, or, you know, but order of magnitude around, megaparsec scale, basically. Yeah. So scales smaller than that, you have an extra force. So what I want to teach you here in my rest of the lectures is, okay, so what are the cosmological observers that I can use to detect this fifth force in these megaparsec scales? I can use very large scales probes as well, like the cosmic microwave background radiation, but that's just like general relativity. So I won't find anything there. But if I look at smaller scales where gravity is stronger, then I can find the differences there. Okay. Yeah. So let's take a pause because it's too, there's no point running. Yeah. Okay.
Okay, thank you very much. Before we have a break, I think Kampi will go somewhere else. And then let's have a group photo between us with the Mota and Kampi also. Let's go down and rearrange yourself in the frame of, and to take a photo. So some of you can take upper. อาจารย์ขึ้นเลยจะได้สูงกว่า โอเค ไม่เป็นไรครับ who is photographer โอเคแทน Before start maybe the fourth lecture, I have something to announce about tomorrow. Most of you, I think, will leave from the dorm, right? So that tomorrow you have to leave the dorm before maybe 12 or something. So that you have to take the racket to here also. So that's some of you maybe have a heavy racket. So that I think in that case I will take my car to take the racket to here. Or if not too heavy, you can take it to the bus. It's okay. But I will tell you later when I take my car to the dorm, and you can take the racket into my car, and then I put it here for most of you who have to leave tomorrow. Yeah. Okay, thank you. Let's.
Hello? Yeah. Okay, so yeah, let's continue. So yes, so unfortunately I won't be able to give my whole lectures, but on Friday I'm giving the colloquium. So maybe many of you are not here, but the colloquium would be a continuation of my lectures. And well, those of you who can hear, that will be very nice.
We have online.
Yeah, online, okay. So I think after these lectures you will understand my colloquium quite well. Because of my colloquium focus a lot of the observations, which I haven't reached yet. I didn't manage to get there. I think I'm a bit too slow, but I think it's better that I go slow. And thanks a lot for the questions. Some of the questions you can ask also here. So because I think many of your questions, I think other students also have. So if you ask, then everybody can learn from your questions. Okay, so we were talking about these linear effects, and what the Newton-Poisson equation tells you is that at very, very large scales, outside the range of the free force, basically the free force doesn't reach those scales, so you just have general relativity. But inside the range of the free force, we have an extra gravity, because you have an extra term, so the potential is 4/3 times more sourced than in the case of general relativity. Okay, so there's a stronger gravitational attraction in there. So that means that at large scales, at least, you will see that there's a clustering of matter which is stronger, at least at megaparsec scales. And you can see that by studying how matter perturbations grow in time. So from the energy momentum tensor, is just the matter perturbations on the background plus the matter density on the background plus the perturbation. Okay? And then when you put in the perturbed energy momentum equation, what you get is something like that. So matter perturbations, they grow proportional to phi dot, which evolves in time. So you can get basically linearly perturbed energy momentum conservation equation. So the 0, component, 0I component. So you get these two equations for how matter perturbations evolved at cosmological scales. So again, using a quasi-static approximation for my extra degree of freedom, that's the equation that you have. And again, as I showed you, that's the Newton-Poisson equation for this f of r theories of gravity. And that means that, again, if I'm going to plot, so this is a figure where on the y-axis, I have the matter perturbations in f of r gravity divided by the matter perturbations in lambda CDM model. Okay, so what I'm showing in the y-axis is the difference of them. So I want to see how much more clustering you get in f of r gravity done with respect to lambda CDM. So that's the y-axis. The x-axis, I have the scale, kappa. Okay, so that's in inverse megaparsec. So here, kappa becomes very large, so that's small scales, while there, this is very large scales. Okay, so we start to see megaparsec scales around here. Okay, so here this is much larger scales. And what I'm plotting, all these lines, they are the deviation from lambda CDM between an f of r model with f of r equal to 0.1 all the way to f of r equal to 10 to the minus 7. Okay, as you can see, when it's 10 to the minus 7, it's almost 0. That's because the deviation from lambda CDM is almost non-existent. Okay, I told you that when this f of r is a very small number, basically this theory recovers general relativity very quickly, with exception to the smaller scales. That's why here there's a small deviations here to lambda CDM at smaller scales. As I increase the value of my f of r today, I'm increasing the deviations from lambda CDM. So what I'm doing here, when I increase the f of r, I don't know if you remember, f of r0 is just the range of your fifth force. So if I increase the f of r, I'm increasing the range of the fifth force, and so it means I'm clustering more matter from larger and larger scales. And that's why if I increase the range of the fifth force, I see all these lines going up. The deviations from lambda CDM, as I go to larger and larger scales, it starts to increase. But then as you can see, all of them, as I go to large, very large scales, they all recover general relativity, because outside the range of the fifth force, I basically have general relativity. Okay? So deviations from lambda CDM occur within the range of the fifth force. This is what it says. Okay, so, and the key property is this f of r parameter. That's my scalar field. You can interpret like that. And the Compton wavelength, basically, of my f of r, the Compton wavelength, changes according to parameters. So it can be from 10 to the minus 4, 10 to the minus 6. That's what I'm showing you. So this is the Compton wavelength. So this is the range of the fifth force as a function of redshift. So my Compton wavelength, that looks like just like in this y-axis. That's the Compton wavelength as a function of redshift. So high redshifts, low redshifts today. Yeah? Low redshift. So this is today, and this is redshift equal to 3 in the past. So as you can see, let's look just at the black line or the red line. Today, the Compton wavelength is larger than in the past. So the range of the fifth force today is a bit larger today than in the past. Yes, the range is larger in the today than in the past. Why is that? Think about the chameleon mechanism. Because you remember the chameleon mechanism? The range of the fifth force changes with the density. Yeah? So why the range of the fifth force today is larger than the range of the fifth force in the past in the universe? It drives the acceleration, that's right. But why the range of the fifth force in the past is smaller? As it is showing you there. There's more density, yes? So the universe in the past is smaller, more dense, so the range of the fifth force is shorter. As the universe grows, the density of the universe decreases, then the range of the fifth force increases. Yes? So because it's the chameleon mechanism. In this f of r gravity, we have the chameleon mechanism. And that's what is telling you this plot. Okay? So the range of the fifth force will become more important today, and it will affect larger and larger scales. Okay? But of course, the range of the fifth force depends if I'm on 10 to the minus 4, 10 to the minus 5. So this is the choice of parameters. So this 10 to the minus 4 f of r today is like around 20 megaparsec. While when the f of r is 10 to the minus 6, is about 2 megaparsec. Okay? So the range of the fifth force depends on the choice of my parameters. Okay? So let's give an example. Very good. So, yeah. So this is just a summary, so I don't need to, I don't think it's okay. Otherwise, I don't need to give you the summary. So something very important is that I've used, in order to show you these plots and to do this calculation, I've assumed linear perturbation theory. So I've assumed that the metric potentials, they are linearized. So I perturb the F4W metric with the two potentials, two Barting potentials, and those I have assumed to be smaller than 1. And that's okay, because in a galaxy, the size of the Barting potentials, those phi and psi in the metric, it's about 10 to the minus 5, even in a galaxy. Okay, so that's okay to perturb the F over W metric linearly. The problem here is that I have also perturbed the matter density. And I have assumed that the matter density, I perturb it linearly as well. So delta M is much smaller than rho density of the universe, of critical density of the universe, the background density. That is true at very large scales, but at small scales, the galaxy is 20 orders of magnitude more dense than the critical density of the universe, so 30 orders of magnitude. So linear perturbations, they break down at galaxy cluster scales. Because rho, the matter densities, basically, it breaks down, it's much, much larger. So these equations are not valid for non-linear structure formation. And what I'm not sure how much time I will have, I will have to show you what are the equations to do non-linear structure formation. Okay, so these equations are only valid at linear structure formation. So if you want to use the cosmic microwave background radiation data, the fluctuations of the CMB, to put constraints on these models, that's okay. You can use linear perturbation theory, and you can use that. If you want to use the linear matter power spectrum, as I will show you next. But if you want to use properties of galaxies to put constraints on the models, then you cannot use these equations. You need to solve them non-linearly, okay? Which I doubt I will have time to explain you that, but okay. Good. So just to give you an example, so if I just want to show you, like using data from supernovae type 1a, the distance to the baryon acoustic oscillations, and the distance to the CMB first peak, the shift parameter, to, for instance, ask the question, how much can I deviate from the Einstein-Hilbert action? So if I include a term where alpha and beta are free parameters, okay? I want just to ask the question, okay, I have the Einstein-Hilbert action, and I include an extra term, proportional to R, to a power of beta, it's a free parameter, and alpha, a free parameter, it's a constant. How much can just the background data tell me, how much can I deviate from the Einstein-Hilbert action, from general relativity? So if I use the supernovae data, what I have is the following. So this is the beta in the y-axis. So beta equal to 0 is there. So that's basically, it's a constant, like that's the cosmological constant, basically. When beta is equal to 0, this is a constant. On the x-axis is alpha. So that's the constant there. So the universe, if beta becomes very large, for these values of alpha, then I have a decelerated expansion. So as you know, this is ruled out by supernovae data. Yeah, and I have an accelerated expansion for this region of the perimeter space, the white part of the perimeter space. So the cosmological constant basically is there, is that cross there. I don't know if you can see it. That's cosmological constant there, more or less. Okay, so the supernovae data tells you that only this red area is viable for this model. Okay, so you can deviate from general relativity in this range of the parameters. Okay, that's what the data is telling you. If you now include some very large scale structure formation, so the peak of the linear matter power spectrum, where the matter power spectrum has a peak, it changes, then it gets constraints to the red region. If you now include the CMB shift parameter, so basically it's also related to the first peak of the CMB, that's how you get constrained. And if you add also the baryon acoustic oscillations, that's what you get as well, the blue area. So the areas start to shrink, the viable regions of these parameters. So it's basically the background cosmology of the universe tells you it's almost general relativity. So you can still have alpha and beta different from lambda CDM, but it's very constrained. Yeah, so at the background level, it's very difficult to distinguish if I'm doing an F of R gravity with lambda CDM. Okay? So as I said, I do not want to make my life complicated to have a model which just behaves like a lambda CDM. I want to have something which has some signature so I can test and rule out the model. That's what science is about. Otherwise, we are not doing science. Yes, I can create a theory with so many parameters that explains everything, even why I raise and lower my hand here now at the moment. Yeah, but that's not the idea of science. Okay, we can try to explain the universe with the minimal amount of parameters. Okay, so that's what I will try to tell you now. What are the observables and why these theories can be ruled out or can be tested with data. Good. So let me now start with my other lectures. Now we start with cosmological probes of modified gravity. At last we got there. Okay? Very good. Okay. So, is it moving? Yes, it is. Good. So, as you have noticed by now, the most important feature of this series of modified gravity is that there is a fifth force. And that means that particles will feel an acceleration, and that acceleration will be given by a general relativity component, so that's the Newtonian potential, if you think in Newtonian terms, plus the gradient of my scalar field times the coupling strength, so the fifth force. Yes, so particles in the universe, that's what they feel. The Newtonian potential plus the fifth force. And what will happen then, if I do structure formation, if I do a simulation of structure formation, what I will see is that structures in the universe, they will cluster in a different way. And of course, the differences are not all that big in these two simulations that I'm showing, because I'm showing you a model, a symmetron model, which is very similar to general relativity. But I will show you other simulations where the difference can be very large. And these models, where the differences are very large, they are basically ruled out. Okay? So this is the whole idea in there. I will tell you how I did these simulations a little bit as well. Okay? But this is my whole idea. So I'm going now to tell you about structure formation probes of theories of modified gravity. And the whole key is this equation here. Again, fifth force plus general relativity, that's what affects particles. Okay, that's why I told you so much about fifth forces. Yeah. So all these theories that I'm going to show you, they all satisfy the background cosmology. All of them. So you don't need to worry about supernova type 1a, whatever. They all satisfy the background constraints, so they all are very similar to lambda CDM at the background level. So the differences will be in structure formation there. Okay. So when I implement the equations of motions into the codes, I'm implementing them, they are n-body codes. In particular, these simulations, they were implemented in the Ramses code and in the J-evolution code. One of them is just a Newtonian code, the Ramses code. So I'm using Newtonian physics. The J-evolution code is a code which is relativistic. So I'm solving as well the Bardeen potential. So the full Einstein equation, fully perturbed Einstein equations. While the Ramses code, I'm just solving the Newtonian equations, which the Newtonian equations are perfect for small scale structures. Yes, we only need relativistic codes when we look to very large scale structures, very, very large scales where gauge choice, etc. are very important. Relativistic effects are important. Or we need also relativistic codes, fully non-relativistic codes when we look at like pulsars or black holes, and we need strong gravity. So all these codes, they assume other Newtonian gravity, or even J-evolution, they assume the weak field limit. Okay, so we cannot simulate black holes or compact objects in there. So it's about cosmological structure formation. There are cosmological numerical codes in there. So usually they have the general relativity, that's the usual equations that you know. General relativity equations, Okay, and the modified gravity, these codes, again, as I told you, they have a scalar field, a scalar degree of freedom. So I'm telling you in the Einstein frame, but I will also show you simulations from the F of R gravity. Okay, but now it's easier just to show you in the Einstein frame. So it's modified gravity. I will have the Einstein equations plus a function from the scalar field. The energy momentum tensor here is 0 because there's nothing there, but here is going to be proportional to the fifth force because now particles, they also feel the fifth force from my scalar field. And since I'm including a scalar degree of freedom, I also need to solve the Klein-Gardner equation for my scalar field. Yes, if I mean I am the metric, I have to include the equation of motion for the metric. If I have a scalar field, I have to include the equation of motion for my scalar field, yes, to be self-consistent. I need to solve all the equations. Okay, so now what I will do to solve these equations, I'm not solving the full Einstein equations. As I said, I'm going to linearize the Einstein equations in terms of the gravity fields. So I'm not solving, I cannot solve for black holes or compact objects. I'm going to do a cosmological simulation. So my metric is close to FRW metric up to the Barton potentials. I linearly perturb the metric because the Barton potential, even in galaxies, as I said, is 10 to the minus 5. So the metric is still very close to Barton potential, but the Mota density is now, when I have rho, I really have rho, and can go up to galaxy scale. So 10 to the 30 critical density of the universe. So I'm not linearizing the code in terms of the Mota density. The Mota density is fully nonlinear, just the Barton potentials. And I'm showing you here just the Ramsez version of the equation. So it's the Newtonian regime kind of the equations. Yeah. So I have a modified Poisson equation because now my field basically fills the matter distribution plus the scalar field, and the particle acceleration, each particle, this is an n-body code, so I have particles, and each particle, they have field and acceleration, the force, and this force is given by the gradient of the Newtonian potential plus the gradient of my scalar field. Okay? Yes, and I have also need to solve the Klein-Gardner equation for the scalar field. And that's a really, well, nothing is very easy, but this one is a bit more standard. People have done that for a quite long time. Lately, in the last 10 years, people start solving this Klein-Gardner equation of the scalar field, solving the scalar field also at the same time as you move the dark matter particles. And this is quite difficult. So the first part that people do, people just assume the quasi-static approximation for the scalar field. So they neglect time derivatives and they just solve the scalar field as just a spatial gradients of the scalar field, because the scalar field is sourced by the scalar field itself, derivatives, and the energy density of the universe. Okay? So you have to solve to know what is the profile of the scalar field, because remember, what I need to know is what is the profile of the scalar field, so I can calculate the gradient, and when I have this gradient, I can calculate the acceleration of the particles, and then I see our matter cluster. Okay? So that's what I did. Lately, in the last 5 years, we are now able to solve also time derivatives for this scalar field. This is quite difficult. It's very expensive numerically to solve. Codes take a very, very long time. But we can do this both in Ramsez, so in the Newtonian limit, and we can do also with the J-evolution code, which naturally solves the full equations of motion, time derivatives both for the Newtonian potentials and for the scalar field as well. But for instance, most of the codes in the literature, they only solve assuming the quasi-static regime. So what we did is that, yeah? Yeah, yes, we have, we don't solve in, you transform it in Fourier space, you do a lot of tricks, yes, it's quite a lot of numerical methods to solve these equations. It's quite complicated, in fact, yes. And when I tell you about dark matter particles, each dark matter particle is like a galaxy. So you cannot really imagine a dark matter particle. Each dark matter particle in the simulations I'm going to show you is 10 to the 6 solar masses. Yes, some of them 10 to the 9 solar masses. So it's a really, when I talk about these particles, it's very large cosmological simulations. Some of the simulations I'll show you, we go down to maybe 10 to the 5, 10 to the 4 solar masses each particle when I want to look at smaller scales. But I'm going to mainly show you very large cosmological scales. Okay? So each particle basically is a galaxy going on.
How do you know that it's safe to linearize the Bardeen?
Sorry? How?
How do you know that it's safe to linearize the Bardeen term?
potential.
The Bardeen potential? Yes. How do I know what?
That it's safe to linearize.
Oh yeah, no, because one thing I can do, because one thing I can do, I just run the simulation and I see what's the value of the Bardeen potential at galaxy scales, and I see it's going to be around 10 to the minus 5. But also from observations, we see that the strength of the gravitational fields is quite small. So matter can be highly nonlinear. The density of matter can be highly nonlinear. So the solar system, we are still on the weak field limit, even in the solar system, and the sun is very compact, you know. So and that's because gravity is a very weak force. So even if matter is highly nonlinear, when you transfer this highly nonlinearity of the matter density into the gravity, to the gravity field, which is the metric, basically, the spin 2, the value is still very small. So that's the Bardeen potential. So even in the solar system, that's 10 to the minus 5. It's a very small value. Yeah. So in order to get values of order 1, so that when you need black holes, you know, so you have huge densities concentrated in a small amount of space. Yeah. So yeah, so gravity in our universe in general, even at galaxy levels, it's linear gravity, let's say. Yes, when I mean matter is nonlinear, so usually in class, because you know then in this Boltzmann code, so in linear perturbation theory, you say that the matter density is the background density plus a delta. And this delta is much smaller than the other one. So here, we don't keep delta, we keep it rho, and we let it grow much, much larger than the critical density of the universe. We just keep it growing. And we keep feeding this rho into this rho, we keep feeding it into the Bardeen potential and into the Klein-Gordon equation as well. But the coupling is so weak, G is such a small number, that basically the Bardeen potential will always be very small. So we are safe on the weak field limit. Yeah. So all these simulations are weak field limit simulations, in fact. That's on cosmology level. Okay? So we just put these equations, we run codes, it takes a long time, lots of computing time, lots of energy, maybe not so good for the environment, but maybe good for science.
Usually how long?
It depends, but some of them can take like a week to run, it depends. So if you just run the GR simulation, very large scales with not so many particles, then they can run in a few minutes. If you want now modify gravity, then you need a couple of days. But then depends if you want to high resolution, so to go to very small scales, then you can take weeks. And if you put baryons, because all simulation I'm going to show you with exception, maybe only in the colloquium, maybe not here. Then if you put baryons, these are only dark matter simulations only. If you put baryons and baryonic physics, then it's take a long time. And I even had simulations which they never reached redshift 0. So I started redshift 20, I run them, and they never got to redshift 0 because it's just too expensive. Yeah. So it can be very long. But you can also just do some quick simulations with codes, and if you have now with GPUs, things can go much faster. So it's quite nice, you know. So it depends, yeah. It depends on your computer, etc. Very good. So the code that we are using, as I said, is the Ramses code, and the simulations I'm going to show, the results I'm going to show you, is basically for f of r gravities and for symmetrons. And I'm going to show you results for 3 choices of the f of r gravity. So they're going to be called f of r 4, 5, and 6. And I'm going to show you results for 3 choices of the f of r gravity. So they're going to be called f of r 4, 5, and 6. And I'm going to show you results for 3 choices of the f of r gravity. So they're going to be called f of r 4, 5, and 6. And I'm going to show you results for 3 choices of the f of r gravity. So they're going to be called f of r 4, 5, and 6. because basically you remember this f of r0, that's the parameter, gives me the Compton wavelength for my f of r field. Is going to be 10 to the minus 4, 10 to the minus 5, 10 to the minus 6. My n, that parameter in my f of r function to get the chameleon, is just equal to 1 in all of them. And so that means that I will have a fifth force, which today, because remember the fifth force changes with redshift, yes? But today the fifth force for f of r4 is about 23 megaparsec, f of r5 is about 7 megaparsec, f of r 10 to the minus 6 is about 2 megaparsec. Okay? So, as I said, one cluster is about megaparsec scales, the usual cluster. And the coupling strength is about, it's always fixed in f of r theories of gravity, it's always 1/3. So the coupling strength is 1/3. What changes for the chameleon f of r is this range, and this range is at the background universe level only. Okay, because when I come to galaxies, this range will change, will become shorter, and when I do an experiment with neutrons bouncing on a mirror, this range should go very, very short, yes, below millimeter scale. Otherwise, these theories would be ruled out by laboratory experiments. So for the symmetron, I'm going to show you results for 4 symmetron models. The symmetron has in fact 3 parameters. So one is the coupling, the strength of the coupling, which is free in the symmetron. I'm going to show models with coupling of strength 1, and only the symmetron C is going to have a coupling of strength 2. So that means that symmetron C has a coupling constant which is 2 times bigger the usual gravity coupling, okay, the usual GR coupling. So it's twice that. The Compton wavelength of the symmetron, so the mass of the symmetron, remember the symmetron has a constant Compton wavelength. I'm going to choose just equal to 1 megaparsec. Okay, and remember the symmetron, that's the model where on Earth and compact objects, this coupling goes to 0. Remember the symmetron is this parabola, so this field goes to 0 in high dense regions, and it becomes this Mexican hat potential in low dense regions, yes? So in the high dense regions, the beta will go to 0. Yes. So the symmetron has what is called a threshold behavior. So we want the effective potential of the symmetron to go from a Mexican hat potential to a parabola as I'm coming to a high dense region. Yes? So when the symmetron basically sees a galaxy like the Milky Way, I want the symmetron to go quickly from the Mexican hat to a parabola. So I screen away my symmetron inside the Milky Way. So I can do experiments in the Milky Way, in the solar system, on Earth. I don't detect the symmetron because the coupling goes to 0. So basically, I have this density threshold which I can choose for the symmetron. I can associate the density threshold of the symmetron to the density of my universe at a different epoch. Yeah, so my universe during Big Bang nucleosynthesis is much dense, and as it grows, the density of the universe goes down. So when the universe is about 0.5 in terms of A, so redshift 2, it gets to a density similar to a galaxy. Okay? So instead of thinking about I'm screening the symmetron at when the density is the galaxy, I can think I'm screening the symmetron at redshift 2, for instance. Okay? So this symmetron field for redshifts below 2, in this case, 0.5, that's about 2, redshift 2. So redshifts of 2 and higher, the symmetron is always screened. So the effective potential is just a parabola, and the field fits in is 0. When the universe, after redshift 2, the universe becomes low density, so the effective potential becomes the Mexican hat, then the symmetron appears. Okay? So that's why sometimes I'm going to show you differences for different redshifts, so different thresholds for the symmetron. Okay? All right, let me show you some things now. Okay. So here I'm showing you now a much more extreme model, as you can see. Yeah. So here I'm showing you two modified gravity models. Yes. This is the scale 100 megaparsec, so this is a much larger scale. So remember, like a galaxy cluster is 1 megaparsec. Yeah. So it's much smaller in these scales. Here is a model, a symmetry model with a very weak coupling, and here is a model with a very strong coupling. And you can see why. Yes, you see that a very strong coupling, you have a phi force which is really strong, so clustering of matter becomes very violent in our universe. Okay? And one way of seeing from the equations, you can think of the phi force as having an effective gravitational constant, and this gravitational constant is 1 for the Newtonian one plus this kind of Yukawa correction, which now you attended my lectures, you know that beta is not really a constant, it's changing with the field, but this is still a good approximation. Okay? So, as you can see, this model of the symmetron is probably ruled out because it's very extreme. Yes? You see these big voids appearing in our universe, matter-related cluster. This is too different from lambda CDM to be valid. So this model with a very strong coupling is ruled out. This one is maybe still valid, but we'll go there. But what I want to tell you is that structure formation depends on the strength of the coupling. And that makes sense. The phi force is proportional to the strength of the coupling and also to the range. So we will see now for the range. Good. Okay. So, yeah, so let me tell you first. So I have this structure formation which is changing in the universe. How do I measure it in practice? I cannot just look at the universe and try to, oh, it's not running. I cannot just look at the stars and the galaxies and try to see whether they create these voids, you know. This is an image that we cannot see in our universe. It takes billions of years for things to go at that level. So how can I then measure, what can I measure out there in the universe in order to compare with my modified theory of gravity? So the way cosmologists do is very simple. We just measure the so-called galaxy correlation function, which is a measure of the degree of how galaxies cluster in the universe. Okay? And that's very simple. This is a very nice animation that I'm showing you. So you take a galaxies, okay, now a universe, and you're just going to do an histogram of the distance between the galaxies, pairs of galaxies. And that's what they do. So you do an histogram, frequency over the separation of the galaxies. You took two pairs of galaxies, you measure the distance, and you put them on this histogram there. So some of the galaxies are very close to each other, other galaxies are quite far away to each other. Yeah? But you will see that in general, this distribution is not random. There are going to be some very specific scales because of the physics there. Yeah? So that's what you do. So that's basically the so-called two-point correlation function between galaxies. So it's a very simple statistical method to measure the clustering of galaxies. And you'll see there's a very specific bump there. It's called the baryon acoustic oscillation bump. I won't go into details there, but you can imagine that for my phi force, if I have a specific range, like for instance, let's say 1 megaparsec, it means that within 1 megaparsec, there should be more clustering of galaxies around 1 megaparsec than galaxies which are at 100 megaparsec. So maybe for phi force modified gravity, there should also be a bump at the scale which is similar to the range of the phi force. So I can use this method to also probe theories of modified gravity. So what I will show you is not so much the two-point correlation function. I will do the Fourier transform of this, and I will use what is called the power spectra. The power spectra is just the Fourier transformation of this two-point correlation function there. Okay? It's just a measuring how galaxies cluster in my universe. Okay? That's what I will show you. Good. And the reason why I'm using this power spectra is because there's lots of data, and this data can be put on the clustering power, the power of clustering as a function of the distance. Since now this is not a distance. Now this is the inverse. So this is the wave number, K, kappa. Okay, so this is very small scales, and this is very large scales. And all these data points come from the CMB, from cluster abundances, lensing, Lyman alpha forest. So these are different cosmological probes of how matter is distributed in my universe at different scales. So CMB, cosmic microwave background radiation, usually it's very, very large scales. Those are the largest scales. If I want to look at Lyman alpha probes, these are basically electronic transitions like within galaxies and galaxy clusters, then I have to come to these very small scales, okay? But I can put all this data together and I can have a very good shape for my Mota pulse spectrum. This is what is called. And I can compare this data with my modified gravity data, because you remember in my simulations there was a lot of clustering. If the clustering is too big, it's going to be outside this data, so I can rule out my theories of modified gravity. So this is what I'm going to show you now, the Mota pulse spectrum for these theories of modified gravity. Okay, so let's think first a non-screen massive modified gravity. So just a scalar field where there is a coupling to matter, beta, and there is a Compton wavelength. So there's a range of the force which is inversely proportional to the mass. Okay, so that's my free force. So here on the y-axis, I'm comparing in percentage of the deviations of the Mota power spectrum. So that's the power spectrum. That's the two-point correlation function in Fourier space between modified gravity and lambda CDM. That's on the y-axis. And here is K. That's just the wave number. So these are small scales. So K equal to 10. That's about 10 megaparsec. Okay, so that's really small scales. K equal to 1 is 1 megaparsec, so galaxy cluster. So here is very, very large scales, 0.1. But yeah, okay. So this plot shows the symmetry model. It's a symmetry model with a length, a Compton wavelength of about 1 megaparsec, and the redshift where symmetry breaking happens. It's a symmetry breaking because it's symmetric parabola, and then it breaks the symmetry when it becomes a Mexican hot potential. Okay. The symmetry breaking happens at redshift 1. Okay, so also it's basically a symmetry model, so it drives the universe acceleration as well. So when coupling is about half of the gravity strength, you see that I have deviations in the clustering of galaxy, especially here at small scales, which is about 2%, 3% from lambda CDM. If I have the symmetron coupled to the matter fields with the same strength of gravity, beta equal to 1, then you can have deviations of about 10%. This is what you see, yeah? So the stronger the coupling, the stronger is the clustering of galaxies for scales which are, as we showed, at smaller scales within the range of the fifth force. That's where deviations become quite strong. Yeah? And what you also see is that this is effective when the Compton wavelength is finite. Here it's just 1 megaparsec. So if I go to scales which are much larger than the Compton wavelength and the range of the force, I recover general relativity. My G effective becomes equal to 1. So for regions, distances smaller than the Compton wavelength, the fifth force is active. So the G effective, the effective gravitational constant, is twice B squared, okay? And that's why you see such a clustering. So now if I compare a long-range force, so here is the same strength, beta equal to 1, beta equals to 0.5, but now the difference between this plot and that one is that this is a long-range force, is 2 megaparsec range. The range of field force is 2 megaparsec, so it's a lighter field. And here is just a 1 megaparsec range. And you can see now that deviations from lambda CDM, they become much, much larger. So we have like 140%, 160% deviation. So huge deviations just because I've increased the range of the fifth force by 1 extra megaparsec. And here as well, I go from a couple of percent to like 20, 30, 40% for the same strength. So the range of the fifth force is a really, really important factor when you do structure formation, because you can lead to very strong deviations. Okay? But again, both these models, they show you if you go to very large scales, scales much larger than the Compton wavelength of the field, you know, deviations, they all go to zero. You see here? You see there? They all go to zero. So the linear matter power spectrum, basically of these models, they basically recover general relativity. Okay? So if you want to test gravity, you want to test gravity at smaller scales, not at the very, very large one. Because the very, very large one, you see the clustering in the universe, which is basically very similar to lambda CDM. Okay? I don't know until what time do I have? I can't remember.
3:20.
3:20. Okay, okay, yeah. So I can do this one. Okay. Okay? So the conclusion here is that the background cosmology, like supernova type 1a, it's indistinguishable from lambda CDM. And the very large scales, so if you test the cosmic microwave background radiation fluctuations or the linear matter power spectrum at very large scales, you can also not detect differences from lambda CDM. So the differences within at scales which are megaparsec, that scales within the range of the fifth force. Okay, another dependence, it's when these modifications of gravity appear. Because remember, we have the screening scale, that's the scale where the fifth force is hidden. So if I change my screening threshold, I will also affect structure formation as well in the universe. So for the case of the symmetron, I have that my G effective now becomes scale dependent. There's a K there, so it means that the value, my G effective, the value of my gravitational constant, so I'm just saying that instead of having Newtonian plus the scalar field phi force, I just put all together and I just say matter cluster with a G effective. Yes, I hope that's clear. Okay? So it depends on the value of my symmetron field, because my symmetron is going to be here, yes, when it is unscreened, and depends on the mass or the range of the symmetron there. Okay? So the symmetron is going to be G is equal to 1 when the symmetron just sits in the minima. Okay, with a high dense early universe, for instance, the density of the universe is very high. And as I come to a lower density universe, I will have my symmetron screening unscreened. So my scalar field will fit one of the values there. And this transition scale, that is a free parameter of my model. So I can try to probe what is this free parameter of my model doing structure formation as well. And this is what I'm trying to show you here. So again, I'm plotting the linear matter, well, the matter power spectrum, not linear because I can go to linear scales. The matter power spectrum, again, the difference between the symmetron and lambda CDM as a function of the scales. So small scales and large scales. And if the symmetron, this threshold is only happening at very high densities, so if my symmetron is active all the way, like let's say to the solar system, then there's big deviations from lambda CDM. That means that my fifth force is active for a very long time in my universe. Yes? If my threshold scale is very low, that means that my symmetron basically is screened almost everywhere in the universe. If my force is not existence almost anywhere in the universe, then it means my deviations from lambda CDM are very small. Okay, in there. Yes? So I can use the matter power spectrum, because it's observable, to try to rule out these models, to see which model fits better the data. And for sure, this symmetron here is going to be ruled out, because the deviations from lambda CDM are quite large. Okay? So I can not only know if the modified theory of gravity is valid or not, I can also put constraints on the model parameters to know. And this is for the symmetron. Now I'm showing you the same for the F of R gravity. Okay, for the F of R gravity, so again, we had three F of R gravities, the 10 to the minus 4, 10 to the minus 5, 10 to the minus 6 parameters. And the 10 to the minus 6 is the model which is very similar to lambda CDM. So you can see the deviations are basically very close to 0. at large scales, for sure, it's very close to 0. As I come to smaller scales within the range of the fifth force, there are some deviations, but very small. But this f of r to the 4, that's a very large, so that's the one with the largest Compton wavelength, 27 megaparsecs or so. Then you can see that deviations are much larger for this f of r gravity. Okay, so this one can be ruled out from just looking at the 2-point correlation functions of galaxies. Okay, in there. Okay, so if I screen at only at very high densities, then it's very easy to detect the deviations from general relativity. Another thing we can do, so now I'm going to give you a list of observations. I know you are more interested on the theory side, but okay, but just to tell you what are the different possibilities, is that galaxy surveys, they look at galaxies at different redshifts. So they do not only look, well, especially they don't look at galaxies at redshift 0, so they usually look at galaxies at redshift 0.3, 0.2, 0.1, and 1.15. So they can look at galaxies, so we have galaxies, catalogs of galaxies at different redshifts. And looking at galaxies at different redshifts, this means you can do something like tomography. You can almost calculate the Mota power spectrum at different redshifts. And that gives you an evolution of clustering of galaxies in the universe. It's like that's like almost seeing a simulation appearing from high redshifts always to redshift 0. And now galaxies cluster along the redshifts. So you can do that, and you can also probe, so in this case is the symmetry model. Again, the idea is always to compare to general relativity. That's the y-axis, and this is always the Mota power spectrum. So you can see how galaxies, the deviations from lambda CDM with respect to redshifts. So if you have a galaxy survey which looks at galaxies at redshift 0.66, for the symmetron, you see that deviations from lambda CDM are very small. And the reason is that at redshift 0.66, the fifth force, maybe it's active, but has been working for a very little time. If you look at galaxies at lower redshifts, 0.25 for instance, then the fifth force has been working for more billions of years, so the clustering of galaxies is more affected and deviations from lambda CDM is bigger. And of course, you can compare, again, different model parameters for the symmetron, for instance. Okay? So, I think the conclusion here is just to say that the 2-point correlation functions of galaxies is a very simple statistical method that astronomers use to calculate how galaxies are distributed per different scales and per redshift, and we can use that as a way of ruling out or testing theories of modified gravity. Even if these theories cannot be distinguished at the background level, because they're very similar to lambda CDM. Okay, good. Yeah, so I will do this one. So we are very excited that, just in 5 minutes I'll be finished. So we are very excited then, okay, wow, we have these theories of modified gravity, like for instance this f of r 10 to the minus 4, that's the green line, which has deviations from lambda CDM of about 40%. For k is about 1 megaparsec is really strong deviations from, so I can use my data from the Mota power spectrum to rule out these theories. And what happens then is that is very promising. We were all very excited to use this, but all the simulations that I've showed you, they have been using only dark matter. Now, I know that the universe, there are other particles in the universe, and in particular, we have neutrinos. And I don't know how is your cosmology, but neutrinos are these, they are relativistic for most part of the universe, then they become non-relativistic nowadays, but neutrinos have zero mass. And the fact that neutrinos have a non-zero mass, they basically, neutrinos wash out structures at smaller scales within the Jeans length of the neutrino. So if I have a universe which is matter is clustering with dark matter, cold dark matter, I have lots of clustering, but if I put neutrinos, neutrinos will wash out structure formation at scales which are quite small. Scales which are basically the Jeans length scale of the neutrinos, which is basically inversely proportional to the neutrino mass. And that means when we redid these simulations for f of r gravities and we included neutrinos, what we found is that my big deviation of my f of r gravity, when I now put, for instance, a massive neutrinos of about 0.3 electron volts, they go at basically, that's the blue line, and that's the red line for the massive neutrinos with 10 to the minus 5. They'll go basically close to 0. You know? So we were all excited. Wow, we can rule out this series of modified gravity just looking at the Mota power spectrum. But then we know we have to take into account neutrinos, and if this happens, basically neutrinos wash out structure. So the extra clustering that I get from the fifth force is counteracted by the fact that we have neutrinos washing out structure. So I'm clustering more, but neutrinos doesn't let that clustering to happen. So we were very disappointed because then we can't use the Mota power spectrum, which was a very simple statistical histogram to calculate that, this modified theories of gravity. So we thought about, okay, but let's calculate the halo abundances, how many halos there are in the universe as a function of its mass. So if I count the number of halos, again, you always compare to general relativity, yes? What's the deviation of the number of halos per mass in my universe? If I have an f of r theory of gravity, like the 10 to the minus 4, I see that there's many halos, more halos in f of r gravity, very massive one, than in lambda CDM. This is the deviation, yes? So because there is a fifth force, so I create bigger halos because there's a fifth force. So I see lots of big halos in f of r gravity, and as I come to very small halos, basically I'm approaching general relativity. So I say, wow, if there's lots of big halos, maybe that's the way we can rule out this series of modified gravity. You just count the number of big halos in the universe, and you say, well, they're not as many as we expect in general in modified gravity, so we can rule out. But again, when you use neutrinos, because we know neutrinos are massive, then they come down again to the regime of general relativity. Okay? So we have here a problem in cosmology, which is this degeneracy between neutrino masses and this series of modified gravity. Because series of modified gravity, they have the extra force, clustering, and neutrinos, they wash out structures in our universe. And yeah, so that's really a problem in there. Okay, I think I will stop now, and then I will tell you some ways. I think it's time, yeah? Yeah. And then on the next lecture, hopefully I will tell you some ways of breaking this degeneracy. Let's look at something else which might break this degeneracy. Yeah, but you have questions.
I don't know why neutrinos wash out these the power, the matter flow.
Yeah. That would take a long time to explain. That's a whole cosmology lecture. But basically you can think of when you write down the equations of clustering of dark matter, for instance, the delta M equation for dark matter clustering, there is no scale. So in principle, from that equation, dark matter can just cluster as much as they want. The neutrinos, they have a given, so they start being relativistic in the early universe. So the velocities are very, okay, so let's write the equation. So one way of intuitive thinking is that neutrinos, the mass is very small. So that means they are relativistic in the early universe, so they move very fast. Yes? So it means they cannot cluster themselves. They will be always being washed out in there. So when you put massive neutrinos on your universe, you are putting some mass. So it means you have to remove a little bit of dark matter mass. And if you remove a little bit of dark matter mass, then there is less gravity, there's less matter, so the clustering is a bit smaller. Okay, so that's one way of intuitively to see. but there's a bit more physics to that, with something called Jeans instability. Yeah, but that will take a bit longer time, yes, to explain. Yeah. Yes.
So the idea of using modified gravity, so you don't include the lambda in the. I mean, it's like in a like newly structured way, right? So it's like representative for the dark energy in some sort.
So the idea of having this modified gravity is that you don't need a cosmological constant. The modification of gravity comes from this extra degree of freedom as a potential that drives the universe acceleration. Yes.
So should it also like somehow be used to explain dark matter in some like?
Yeah. Yes, people use these modified theories of gravity to also explain dark matter. But usually for that, these models, they do not work because, for instance, they can explain galaxy rotation curves because there's more acceleration, so you can explain the galaxy rotation curves, why stars move faster even when they are very far away from the galaxy center. But they cannot explain lensing. And that's something that I will tell you either here, next lecture, or in the colloquium. You have to listen to me, that these theories do not affect the photons' geodesics. So lensing in these theories is the same as in general relativity. And one of the ways we detect dark matter is because we see a lot of lensing. Photons bend a lot in regions of the universe where there's not enough matter. And these theories of modified gravity, they affect the acceleration of massive particles, non-relativistic particles, but they do not affect the photons. And that's why they're called conformal field theories, and because the scalar field couples to the trace of the energy momentum tensor, and the trace of relativistic particles is 0. Yeah, the trace is just rho minus 3p. So the pressure is 1/3, so density, so the trace is 0 for photons. So these theories that I'm showing you here, they cannot explain dark matter. At least they cannot explain lensing phenomena in dark matter.
So that's why you still assume the usual like dark matter.
Yes, that's right. Yes.
And also the simulation perspective. So normally you don't use just one simulation, right? You use like many simulations and select the like appropriate seed and stuff.
Yes. So there's several. Yes, that's right. Yeah.
And I mean, I don't quite get the logic of that. So you have to select the seed that fits most, and then.
No. Now you're talking about simulations that form galaxies, probably. Like really small scale, spiral arms and things like that. You might be talking about that. I'm not doing that kind of simulation. These ones are very cosmological ones. So the way we run these simulations, we start with the very early universe. We put these equations, the full equations, linearly perturbed, so no approximations. We put it in a Boltzmann code, like, I don't know if you heard of class or CLAMB or CAMB or, yeah. So you put it on a Boltzmann code, you integrate those equations with neutrinos, radiation, everything, up to redshift 50 or 20. At that point, we have a power spectra, which matches quite well what we observe, and we start the n-body simulation, the nonlinear regime, from that point onwards. Yes?
So it's more precise in that way.
It's more precise, yes. But the seeds that we talk about, just because you have one Mota power spectrum, there are several ways of realizing the Mota power spectrum, because it's a statistical quantity. So that's why we have different seeds lead to the same Mota power spectrum. So you can play with different seeds, so different initial conditions, let's say, for the position of the particles, but they all have the same power spectra, which fits, the CMB that we see, for instance. And then you start your simulation there. but then I'm not interested because I don't form galaxies. Each dark matter particle is a galaxy for me, each particle here. So I'm not concerned about small, very small scale structures. No. No.
Any more questions?
A little bit more. So like, I was wondering, you are trying to compute the deviation from LCDM model, but why don't you just compare to the real data directly?
Yeah, no, that's right. Yeah, we compared to the real data. We'll show you a bit later. But at least here, when you compare it to the lambda CDM, you understand the effects of the fifth force. You know, you see the fifth force is very strong. There's a peak here, so it's about 1 megaparsec. And you say, yes, it makes sense because the range of my fifth force is about megaparsec. So this is just to learn and to teach you. Of course, at the end of the day, you put the data and you see this f of R4 model is ruled out on the data. Even with the neutrinos, yeah. So yeah, even with the neutrinos, yes. So you can do that directly with the data.
There are two peaks on the baryon acoustic oscillation.
Oscillation, yes.
The first peak we can use as a standard ruler. So how about the second peak?
You mean to put constraints on this series of...
The figure of the baryon acoustic peak.
Yes, that peak, yeah.
The first peak we can use as the standard ruler. So what about the second peak? What should the meaning of the second peak?
No, the short answer, I don't know. That's the short answer I should tell you. But you can try to fit the baryon acoustic oscillation on these models as well to see if in real space, not in free space, if it fits the second peak as well. But usually, in fact, these baryon acoustic oscillations, it's still at linear, quasi-nonlinear scales. So it's still the viable modified gravity theories, they still fit very well the baryon acoustic oscillation peaks, I would say, even the second one. But I'm not sure. Maybe it's a good idea to look at the fit to the second peak, yes. But maybe you know better than me how to use it, because I don't know. I never used it, yeah. Okay.
Okay, any more questions? So if no more questions, please thank David again, and then we come back at T45, and then we have another 1 hour lecture. Okay, so that is supposed to finish 4:45. Okay. Okay.
Yeah, maybe I don't
Yes.
know where speak to. Okay, so yeah, welcome to the fourth one or the fifth one.
Fifth one.
Wow, okay.
Yes.
Okay, yeah. Well, okay, everyone. Okay, welcome to the fifth lecture, the last lecture of Professor David Mota. Yeah, please welcome. Please.
Thank you. Well, this is still, yeah, I'm halfway. But okay, but I can't teach everything. So, as we saw that these kind of probes are very promising because it's clustering of matter in the universe, and if there's a fifth force, you should see big deviations from the way matter clusters in the universe. But if you take into account more realistic models of the universe, where, for instance, there are massive neutrinos, they are not as good as we expected. So it's important to think about other kind of probes, which you would be more independent of, for instance, massive neutrinos, etc. And one of them, so there are several nonlinear probes. In my colloquium, I will tell you about some other ones, but at least I will tell you about one of them now, which is the gravitational redshift. So the gravitational redshift is a phenomena that was predicted by general relativity, and as you know, basically a photon climbing out of a gravitational well, it redshifts, so it loses energy. Okay, so in cosmology we can use it in order to measure, for instance, the potential wells in the universe. So where galaxies and galaxy clusters sit, they will create a gravitational well. So photons coming from those regions, they will be redshifted. So the whole idea of the gravitational redshifts in clusters, that's what I'm going to talk about. So we have a cluster, so we have a group of galaxies distributed in my cluster, and they will create a gravitational well. So usually there's a galaxy, a very big galaxy, usually in the center of the cluster, a very massive one, and then other galaxies which basically go to the outskirts of the clustering. So there is a gravitational well here, with a deep central value for the gravitational well. That's the deepest point, usually in a big, massive galaxy cluster, and this gravitational well, basically, what people do is that we can measure from the theoretical point of view, and then this was really measured a few years ago, the redshift of photons, for instance, coming from the central galaxy, and comparing with the photons, redshift of photons coming from other parts of the gravitational well. And the difference between those redshifts gives you a measure of the difference with respect to the potential well. Okay? So that's basically a very nice way of measuring potential wells. And as you can imagine, these theories of modified gravity, they will change the potential well as well. So there might be something we can do with these observations of the gravitational well redshift to probe, to detect deviations from general relativity. So what we'll do is that if you have a measurement of the potential well, you can also have a measurement of the mass distribution in a galaxy cluster. So you can compute the matter profile of the density profile of galaxy clusters. This is important. I won't show you here, but when we do these simulations that I showed you, these n-body simulations, we can find halos, and we can also compute the density profile of the matter profile of dark matter halos. And you know, well, maybe you don't. In general relativity, there is the so-called Navarro-Franken-White density profile for dark matter, for cold dark matter. If you have a modified theory of gravity, you will modify this Navarro-Franken-White profile. And so there are many different kinds of probes. For instance, you can use lensing in order to compute the profile of dark matter halos. So, so calculating profiles of dark matter halos of galaxy clusters is something that is very useful to test theories of modified gravity. So here I'm just going to focus on the gravitational redshift of the cluster, and I won't be talking about dark matter profiles, at least here. So the gravitational redshift is, in fact, can be thought about. We just multiply these gravitational redshifts, so the difference in the potential with the speed of light. So we get it. Usually, people measure it as called like a Doppler effect kind of effect. So the velocity, the gravitational velocity of the photons. Of course, it's not a velocity; it's just a gravitational redshift. But it's going to be the Vg quantity is going to show up in my plots. All right. Okay. So if I have general relativity, I can plot what is this velocity. So basically, it's the redshift, the difference in redshift between a photon in the center coming out from this massive galaxy in the center of the gravitational well with respect to a photon along this gravitational potential. Okay, as a function. So that's it's measured in kilometers per second gravitational redshift. That's just some commutative units. And here I'm showing you the gravitational redshift as a function of the radius. So if I'm here in the center of the radius, the gravitational redshift is quite small. And the reason is because I'm looking at the photon, which is coming from a galaxy, which is very close to the center. So phi minus phi c is almost the same. Yes? If I go to the outskirts of my halo, of my dark matter halo, of my galaxy cluster, I'm going to measure redshifts of photons which are coming from the outskirts of the halo. So the difference in these photons, in the redshift, they're almost not redshift. Basically, photons which are already on the outskirts of the halo, they're almost not redshift with respect to photons which are coming from deep inside the halo. Okay, and assuming the Navarro-Franken-White profile, which is a universal profile, if you have general relativity in cold dark matter, that's usually the profile that you have in halos, you have that basically you get a universal kind of a function for the gravitational redshift, and that's the universal function that you have, which basically depend on the mass of the cluster. So for a given mass of the cluster, you have a quite well-defined gravitational redshift curve. And that's basically what this arrow bars tells you, and these lines tells you if I have a halo, which is about 10 to the 14 to the 10 to the 14.5 solar masses, so that's a huge halo, that's a very, very, very big halo. That's the curve for the gravitational redshift, assuming the Navarro-Franken-White profile. If you have lighter halos, smaller halos, and if you go to 10 to the 12, 10 to the 13, your gravitational redshift is a bit smaller. Yes, because if you have a smaller halo, there's less matter, so the potential will be less deep. If the halo is very big, very deep halo, so then the gravitational redshift can be very large, especially in the edges. Okay? So that's for what we have for general relativity, or lambda CDM, let's call. Now we have here a modified theory of gravity. So what we expect is that due to the fifth force, there is more clustering of matter. So if general relativity, that's the potential well for general relativity, then if I have a modified theory of gravity, then due to the fifth force, this potential well will be deeper than the GR1. GR for general relativity. Yeah? So we have a deeper gravitational well. So that means I will have, in principle, a higher gravitational redshift in there from the photons. Yes? So the difference in gravitational well for modified gravity should be larger than the difference of the gravitational well in lambda CDM. So the difference from this center galaxy to this one, for instance, in the edge. Yes? So the difference in gravitational well should be larger, and then it means that the relative deviation, again, I always compare to the expected value that I should get in general relativity. Yes, that's the way I'm giving these lectures now, always compare to general relativity. So I should get a gravitational redshift for modified gravity, which should be larger than 0, because this value should be larger than the lambda CDM1. Okay, that's what I expect from lambda CDM and from modified gravity. And what people did, since I told you a few years ago now is already 15 years or 20 years, yeah, that's what happened. People have measurements of the gravitational redshift for clusters. These are the data points, huge error bars, but it was a very big event because gravitational redshift was just a theoretical thing, you know, like at cluster level. We could measure it on the Earth and the solar system, but not at cluster level. So they got these 4 points here, and they did the gravitational redshift as a function of the radius of a given cluster. Okay, this is what it's showing, and we have the general relativity line. That's the red line here. Okay, this is an F of R gravity here. Okay, this F of R gravity, it doesn't have a screening mechanism, it's just a simple F of R gravity. And we have a theory of gravity, which is called the Teves. So it's a theory of gravity where they include a scalar field, a vector field, and the tensor field into the gravity sector. Yeah, so not just a scalar field as I'm doing, they have the three fields there. And that's a theory which is very promising to explain, to be an alternative to dark matter. So we don't have dark matter, you basically, dark matter, or the effects of dark matter comes from the inclusion of this tensor field, vector field, and scalar field. And with Teves, you could explain very well galaxy rotation curves, because there's a fifth force, because of the scalar field and the vector field, in fact. And we could also explain lensing, because Teves is a disformal theory of gravity, which you mentioned before. It's a disformal theory of gravity, so that means that we change the null geodesics. So the photons path, they change, and we can explain lensing within Teves. But if you can see here, Teves is really bad to explain the data that we observe from the gravitational redshift. So it's kind of ruled out, well, not completely, but you have this data point which is quite high up, you have this one which is quite high up, this one is okayish, this one is borderline. So Teves from the gravitational redshift says that Teves is not a good theory to explain gravitational redshift. We have other problems with Teves, but I don't have time to talk here. So gravitational redshift is something that, what I want to say is that it's there, it's a measurement, and people have been using it to rule out these theories of modified gravity. So, okay, so let's try to apply these gravitational redshift measurements into the theories of modified gravity that I told you about, in particular the F of R and the symmetron models. Okay, so we have to remember that we have three regimes in terms of the screening mechanism, yes? And this can be very easily explained from these three different types of F of R gravity. So the F of R4, remember the coupling in F of R is always the same. It's 1/3 of the gravity strength. That's fixed for F of R gravities. So what changes is the range of the force, and that's the chameleon mechanism, yes? So at cosmological scales, the F of R4 today is about 24 megaparsec, F of R4 is about 7 megaparsec, and F of R6 is about 2 megaparsec. So what we have is that the F of R6 does not change so much the profile of galaxy clusters, okay? I could show you the simulations, but you see the F of R6 has a profile which is very similar to the Navarro-Franken-White profile. So basically, the shape of the gravitational potential for a dark matter halo is very similar, F of R6, with general relativity. Now, the F of R4, on the other hand, it's very strong. It's a very strong modification to gravity because the range is very large and it's not screened in these galaxy clusters. So we have a very strong deviations from general relativity, so the potential well becomes very deep, and so we have a much larger gravitational redshift effect than in general relativity. And then you have the third possibility, in fact, which is kind of a partial screening kind of behavior. So my F of R5, where the range is 7 megaparsec, is a very strange theory because in the center of the cluster, it doesn't really create a very deep gravitational well, but on the edges, it creates some deviations from general relativity because general relativity is this line there in there. You know, so it's a very strange kind of behavior, and it changes the NFW profile, in fact, on the gravity. So, as you can see, there are some in F of R6. I don't expect to see, you know, to use the gravitational redshift to rule out F of R6 because it's pretty much the same as general relativity. But F of R4, I might see some very strong effects, and is this partial screening for F of R5. There might be something there to look at. Okay? So let's try to look at this. So we have these 3 screening regimes for our 3 models from our simulation. So what we do, we basically simulate this. Again, it's an n-body simulation where we start at redshift 20, we evolve the simulation to the particles up to redshift 0. The particles are distributed in our box, simulation box, and we find using halo finder, so we find specific algorithms to find halos in our simulation box. So halos are basically groups of particles, dark matter particles, all together. And these dark matter particles are distributed in profiles, so I can calculate how the dark matter particle is distributed, but I can also calculate from the simulations what's the profile of my gravitational potential there. Okay? So what I see is that if I'm going to try to find what is the phi force, the acceleration that the particles feel of the phi force as a function of the radius from the center of my cluster. Okay, so this is the center of my cluster, and goes out when the radius is equal to 1. It means the radius is the so-called video radius. I don't know what is your astrophysics knowledge. Basically, structures universe, usually they cluster up to they reach the virial, when the virial theorem is satisfied. It's a relation between the kinetic energy and the potential energy. Okay, so when you reach this virial relation, in principle you form a stable cluster and a stable structure. In reality, it's difficult to get virial clusters, relaxed clusters, but in n-body simulations it's easy, yes, because we can just calculate what is the kinetic energy, potential energy, so we find what is the virial radius for these clusters. So this is what happens. So this is the center of the cluster, and this is the outskirts of the cluster. So as you can see, when we have my f of r6, basically this force is screened from the virial radius all the way to the center of the cluster. The phi force is completely screened, so I don't see any effects on the shape of my gravitational potential. It's just the general relativity one, because the phi force is equal to 0 basically everywhere there. On the no screening, so the f of r4, you see that the phi force is very strong, because the phi force, even inside this halo is 10 to the 14 solar masses, so it's a very big galaxy cluster. It's a huge one. So this halo, basically the phi force is quite active, so that's why I have a very strong phi force, and the size of my gravitational potential is very deep. Yeah, so there's no screening and very strong deviations from lambda CDM. And then I have this intermediated case, which is the partial screening, where up to 0.1 of the virial radius, basically you have the phi force, and then the phi force is completely screened inside the cluster. So what are the predictions then? So we did now the simulations, and what we did, we predicted what would be the gravitational redshift of photons coming out from our dark matter halos. Okay? And what we found is precisely this value here. So here I'm again calculating what is the predicted gravitational redshift. Here, that's the y-axis. Again, comparing with lambda CDM. Yes? So the 0 means is basically, that's lambda CDM. Here, no deviations from lambda CDM. And this is as a function, again, from the center of the cluster all the way to the outskirts of the cluster. Okay? So what we have is that when I have a theory which is fully screened, like a theory where the Compton wavelength is just 2 megaparsec, I have that I don't see many deviations from lambda CDM in there. A theory which there's no screening almost, then I can see deviations of about 40 to 50%. Okay, so these theories can be ruled out or can be detected if we have accurate gravitational redshift probes. And then we have this very strange phenomena where we have a negative kind of gravitational redshift for this series which are partially screened there. So we have a negative, so we have less redshift done in lambda CDM. And this is quite interesting. So at the time that we wrote this paper, it's already now a few years old, we were, okay, these theories are also ruled out because we can't, I think we will never get any kind of negative gravitational redshift. But there are some articles that came out last year in the beginning of 2025 and another one this year, which show a very strange phenomena that nobody is able to explain, which are when CMB photons go into into potential wells where we have galaxies. This is called basically the ISW effect. When these photons come out of the potential well, they should also be redshifted. And in fact, so the photons, the CMB photons, they travel, they enter the potential well. As they enter the potential well, they gain energy, yes, and then when they climb out, they lose energy. So if there is no dark energy in our universe, so if the evolution of the potential well is fixed, basically the energy that they gain is equal to the energy that they lose. So when they go out, the photon did not lose or gain any energy. If there is dark energy, when the photon enters the potential well, gains energy. But then if dark energy starts, the potential well is basically pushed apart a bit because of the repulsion of dark energy, so the potential well decreases. And that means when the photons climb out of the potential well, they will lose energy, but not as much as they gained. So the photons of the CMB are a bit hotter, in fact. Okay? Because the photons of the CMB, they come with a given frequency, they gain energy, they lose a little bit, but since they gain much more, when they come out, they're a bit hotter. And this is what we expect with a universe with dark energy. Okay? And what these two articles found is that the CMB photons are coming colder. So for some reason, there is something strange when these CMB photons come out. So it's against our dark energy models, and maybe models with modified gravity, they could explain this phenomena. Here looking at this gravitational redshift, because it seems that the photons will gain some kind of energy in there. But this is just pure speculation. This is just to give ideas if some of the students want to look into that there. Okay, so that's basically something that I want to show. And the signature that I want to show is that you see this, there is this trend where if we are in the outskirts of the cluster, we recover general relativity because the gravitational redshift goes to 0. But if you are inside the cluster, we deviate a lot from general relativity. And that's an important one. It comes from the screening. Because remember, the screening, the force changes its range depending on the environment that they have. But I will show you something else a bit later. Okay, so let me... So let me get, maybe since we are more on the theory side, I will just show something else because I don't have much time. But since many of you are theoretical students, I will try to finish with some theory. So there's another way. I won't spend too many details. I will go quickly on this. Which is probing modified theories of gravity with the cosmic web. So the cosmic web basically is just the distribution of matter in our universe. And the cosmic web, when you look at matter in our universe, there are different structures. You know, we have halos, basically galaxy cluster or dark matter halos, which are basically over dense regions. We have voids, so we have under dense regions, where there's almost nothing, so the density in voids is below the critical density of the universe. And then you have filaments, which usually are these structures that connect, for instance, dark matter halos, these very overdense regions. And all these three types of structures, they're very promising probes of modified gravity. So in the halos, you can measure the gravitational redshift that I just told you, but then in voids and filaments, they have some other features which are quite interesting. Okay? So filaments, these are structures which basically we can look at them, we can observe them by looking at galaxies and how galaxies are distributed in along these lines, basically, of galaxies, yes? And filaments, they have these kind of three properties. One is the length of the filament, so you can see galaxies align until they reach a very big overdensity. The other one is the width of the filament. And here I'm going to define the width. It's a region, it's very difficult to define, but it's a region which is going to be about 10 times the critical density of the universe. So I start in the center of the filament with a high density, and I'm going out and see when this density drops below 10 times the critical density of the universe. That's the width of my filament. And I have the mass of my filament. So it's basically the number of particles that I have inside in this region of the filament, in this volume. Okay, so that gives me the mass of the filaments. And I can use these three properties of the filaments to try to see what happens to these three properties with respect to modified gravity, because we have the free force, etc. Okay, so one thing that we find, again, this is all results. So this is a pure theoretical. It's very difficult to detect filaments in the universe. Okay, so it's really difficult. So these are all pure theoretical results. That the idea is that in the future, when astronomers can do these kind of measurements, whether these are probing, we can probe modified gravity or not with them. Okay, so what we can find is that if we look at the symmetron, the number of filaments and the size of the filaments, so that's on the x-axis we have the length of the filaments, and that's the number of filaments with that length. Filaments are usually shorter in theories of modified gravity. Okay, and the reason is because since there is the fifth force, it means then that the filaments, there's more clustering, so the filaments will not be so long, but will be a bit more compact. So it's natural that filaments of modified gravity, as you can see, there are more filaments on the symmetron model than on the lambda CDM black line. So filaments are shorter in modified gravity. Again, filaments are also a bit thicker in modified gravity. And again, it's because since I cluster more, I can see that the filaments is very difficult to drop below this 10 times the critical density of the universe. So I will have thicker filaments in my universe. There's more matter coming into the filament. So that's why when I show you the number of filaments as a function of the thickness, there's more symmetron filaments with a thickness of about 1 megaparsec. Again, that's the range of the fifth force usually. So there's more filaments than in lambda CDM as well. And if I look at the number of filaments that there are in the universe, I also can find that there are more massive filaments in our universe, filaments which have masses of about 10 to the 13, 10 to the 14. Of course, if I go to very massive filaments, then I recover general relativity. And the reason is that when the filament becomes very massive, the fifth force is screened. Remember, if I put a lot of mass in one region, the fifth force disappears. So the fifth force is less screened when I have small filaments than when I have very massive filaments. Yeah, so there's more matter, but as I start to accumulate too much matter, the screening mechanism kicks in, and the fifth force vanishes, and I just recover general relativity. Okay, so I will try to jump because I want to tell you something about this. So this is my last other probe, and then I'll jump again to something theoretical that I want to tell you about. So one of the most promising probes of modified gravity is voids. And the reason is because the fifth force is screened in overdensities. In voids, it should be very active. So if we can use voids to try to detect this fifth force, that's the most promising place that we have. Okay? So voids are really very promising probes. There is a problem of voids though, is that voids are very difficult to detect because there's nothing there. Yes, the fifth force, for me to detect the fifth force, I need to see two particles attracting each other. But when I look in voids, there's no galaxies, there's nothing there. So what can I measure there? So we have this, unfortunately, we have this catch-22 kind of situation. So, but people still try, okay, let's look at voids. we can count the number of voids on modified theories of gravity. We can see how big they are. So you can see in modified theories of gravity, voids are very large. So we can count how many, how large they are, how empty they are. At least those properties we can try to measure. And this is what I'm just going to show you. So another thing, so voids, we can look at them via galaxies. So if we see galaxies in some region of the universe and nothing there, it means it's a void. Well, maybe there are galaxies there, we can't just see them because they're too dim. So that's a problem as well. But the other way of detecting voids is via lensing, because we might have dark matter filaments around, or dark matter halos. They might not have galaxies, but if I do lensing analysis of some region of the universe, I might see bending of light, so I might detect voids as well with lensing. So the Euclid satellite, which I'm part of, it's one of the aims. It's like we're going to use lensing data to try to detect voids in our universe and use voids to test theories of modified gravity. So one is to look at galaxies, but there are not many galaxies in voids, so it's a problem. But lensing could be a promising probe if there is dark matter there. Okay? So again, if we use voids, for instance, using lensing methods, yeah. So the fifth force, since it's a scalar force in this my case that I'm using, is always attractive. So there won't be repulsive effects. In order to have a repulsive force with a scalar field, usually you need a non-standard kinetic term or some negative mass, so that might lead to tachyonic effects. So usually scalar tensor theories, we have attractive forces. We create very large voids because basically we compress matter a lot. And when you compress matter, you are removing matter from some region of the universe to put all the matter compressed. So that's why voids are not created because of a repulsive force. Voids are created because I just put all the matter concentrated in the halos. If that's the reason for your question. Maybe it was, yeah. With vector fields, vector tensor theories of gravity, you can get repulsive forces. But this is outside my lecture. Yeah. Okay, so we can have like different, for instance, we can have different theories of gravity, like F of R. If I count the number of voids, for instance, I can have, and the number of voids as a function of their size, how big they are. In usually modified theories of gravity, voids are larger. And that's the simulation that you just saw, yes? On my simulation, that simulation was huge voids, yes? So if I count how many big voids there are, usually in modified gravity, there are many more big voids, like with 10 to 12 megaparsec, even larger. F of R gravity, there's also a lot of big voids than in general relativity, okay? So, and that you can measure maybe with lensing. Now, using galaxies, it's not very promising. Of course, galaxies, it's easy because we can see the light from galaxies, but there are not many galaxies in void, so it's a bit difficult. Then all these void abundances, they all get mixed up together. So it's very difficult to distinguish modified gravity and voids if we take into account, if we try to use galaxies. So we really need to use dark matter and lensing and not observe directly the galaxies. Okay, I think I would like, yes, I would like to tell you, maybe go back on the theory on my last lecture, just so I don't give you a wrong impression. So people usually say, okay, I have a theory of modified gravity. As long as I have a screening mechanism, everything is fine. So I can just come up with a crazy theory of modified gravity. And yes-ish, that's correct, but we need to take into account when you have your own screening mechanism, you should do your calculations correctly, because it might not be always true that the chameleon or the symmetron or the Weinstein screening mechanism works as well as you might think. So there are all these modified theories of gravity, and as I said, they're only viable because of screening mechanism. So let me try. Yeah. So one of the key properties why this series of modified gravity are so tightly constrained is because of the equivalence principle, and it's the equivalence between the two Barton potentials, phi and psi. Okay? And basically, phi, it comes from the 0,0 component of the metric, and that's the one that's going to be responsible for the acceleration of the particles, and the psi is going to be responsible also by the photons. So light feels both phi and psi, the sum in fact of the two Barton potentials, called also the Weyl potential. Okay, so that's fine. Now in our solar system, when you calculate in general relativity what the metric should be in our solar system, basically we have the weak field approximation. So we just have the mass, that's basically the mass of the sun over the density over R, and both in this side, both for phi and psi, because in general relativity they are just the same. So the way of testing modified theories of gravity that violate that condition, that psi and phi are not the same, is basically to introduce this so-called ppn gamma parameter. Okay, and that's basically a measure of how much space is covered by unit of time, and it's a measure how different the phi and psi potential are. So we know in general relativity they should be the same. Okay, so this is basically, I just wrote the metric in the weak field limit. From general relativity you have these ones. Okay, good. So people can use light signals, in particular the Cassini probe, the Cassini satellite can send us a light signal. This light signal will travel through the sun potential well and it will bend, okay, because of lensing. And the bending will come because I have this G00 component potential and the Gij potential. Okay, so and now the Gij, in general relativity I put this gamma here, and that's going to be my parameterization for my screening mechanism. So the angle that light will bend is going to be basically proportional to this quantity, okay, 2 times 1 plus gamma, the mass of the sun, because that's the planets, we can neglect it, over the distance, and that's basically 1 plus gamma divided by 2 by the GR expectation, gamma there. Okay, so what we have for Newtonian gravity, gamma is equal to 0, and that's the way Einstein ruled out Newtonian gravity in the solar system, because basically the value that we get is gamma GR, is not the half of gamma GR, that would be your Newtonian part. And for general relativity, basically your gamma is just equal to 1. Okay, so the bending of light is just the GR1. Okay, that's the theory, but we have now the Cassini probe who show us how much this gamma is. Okay, and the Cassini probe basically gave us a measurement of gamma to be close to 1 up to 10 to the minus 5. Okay, so this is an experiment that we did with the Cassini probe. So it means if I'm going to deviate phi minus psi, you know, if the phi and the psi potentials, the two Barton potentials, if they are different in the solar system, they cannot be more different than 10 to the minus 5. Okay, because remember, in general relativity, that's different is equal to 0. But for instance, in the symmetron model, if you calculate what is the profile of the scalar field for gamma, gamma minus phi is close to phi square. There's the psi field. It's a bit of a more of a complicated function, but it's not 0, because unless the scalar field is equal to 0 in the solar system. Okay? For the chameleon, of the f of r gravity, gamma minus psi is proportional basically to the gradient of the f of r part divided by psi. Okay, so it's not 0. So we can use basically this 10 to the minus 5 to put constraints on the chameleon and on the symmetron. And the way, if you remember what we did, we got the equation of motion for my scalar field. You remember, just the Klein-Gordon equation for my scalar field from my action. Yes, that's the usual action. And I calculated the profile of my scalar field for a given mass over density, the profile. And if I have the potential, the solution of my Klein-Gordon equation in my solar system, then I can basically calculate what is gamma. Okay? So that's what I did. And what people usually do, and that's where the big problem in fact is that people assume the quasi-static approximation. So when they solve the Klein-Gordon equation for the scalar field, they neglect the time derivatives and they only consider the spatial derivatives. So the Klein-Gordon equation is not just that, the Klein-Gordon equation also includes time derivatives there. But we usually say, I also say, we live in a virialized region, so the solar system is a stable, relaxed system, so it's not going anywhere, it's not going to disappear and not colliding anything with anything. So it's a quite stable system in terms of the mass. It's basically the sun that plays a role. So the quasi-static approximation should be a good approximation in the solar system. And that's in fact the case. You have just the sun there. There's no other big stars crossing our solar system, no other things. So it should be a very good approximation. And so what people do, they calculate the profile of the Newtonian potential and of the scalar field in our solar system. Yeah, by solving basically what we did, the Klein-Gordon equation, assuming the static approximation, spherical symmetry, etc., etc. Okay, so what we did basically is that in this case, the phi force again is the gradient of my Newtonian potential and the gradient of my scalar field. Okay, so that was the whole issue. So we need to screen away this thing because my gradient of my scalar field is going to come as the difference here in E f of r gravity and on my symmetron as well. Okay. So, yeah, we are almost running on time. So I will skip a little bit. So what we do basically is that we have, due to the screening mechanism, when we calculate the value of the phi force, the gradient of the force basically is suppressed by there. For instance, for the symmetron, remember that when we come to the minima, a very high density region, the potential is a parabola. So the symmetron comes to zero. Yes, so the field disappears. And for the chameleon, the field becomes very short range. So basically, we don't see the gradient of this field. And so that's the way. Okay? So that's, people are very happy because for the symmetron, phi is equal to zero. So all this term becomes zero. Yes? And for the chameleon, basically, the range becomes very short, so this gradient is very small. So that's why we are very happy. That's assuming the quasi-static approximation. What's the problem? And that's how I want to finish my lecture. The problem is that although the solar system is a virialized system and the quasi-static approximation works very well, outside the solar system, many events happened. And events that happen are, for instance, supernovae going off. We know there are supernovae going off even in our galaxy. And when a supernovae goes off, basically what happens is that if I have a chameleon field, which is, for instance, completely screening the supernovae, okay, and screening our galaxy, this chameleon field will have a potential that suddenly, when the supernova goes off, it's in here, and when it goes off, all the matter is distributed very quickly throughout the universe. So the chameleon goes from this minima to that one extremely quickly, and there's an energy, a wave that is created. Yes, from the minimum of the potential, and in a fraction of a second, all this matter from the supernova disappears. So the chameleon field will jump from one minimum to the other one. And this jump will create, by my scalar field profile, which was fixed, basically starts to oscillate. And my chameleon field is connected all over the universe. It's a continuous scalar field. So these waves propagate throughout the universe. And if I have a supernova in my galaxy, they will propagate in my galaxy, will enter the solar system, and will affect the profile of my chameleon field, which was very nicely before quasi-static. There is more as well. For the symmetron, there's another effect, which is the effect coming from domain walls. So maybe not of you know what a domain wall is, but basically the fact that the symmetron, when the density is very high, is in here, and when the density becomes very low in the universe, the symmetron will acquire one minima, one vacuum expectation value, or another one. It means in some parts of the universe, so this is a simulation, where you see the value of the scalar field. Green means it's in this minima, let's call it -1, and yellow or orange means it's in another minima. So in some regions of the universe, the scalar field goes to one minima, and other regions of the universe, the scalar field goes to another minima. So in between these regions, we have something which is called a topological defect, and in particular something called a domain wall, in this case for these symmetrons. So domain walls, they trap energy, and they can trap a lot of energy. So when these domain walls collide with each other, they break. And when they break, they release energy. So if I have my symmetron field, which has a static configuration profile, these domain walls will break each other because they will collide with each other in the universe and will propagate again, and they might spoil the profile of the scalar field again. So in the solar system, when we use the quasi-static approximation to solve our equations for my modified theories of gravity and say, oh, it's safe, there's a chameleon screening mechanism, there's a symmetron, there's a Weinstein, I'm using the quasi-static approximation. And it's true that this system is really nice and static and visualized in the solar system, but outside in our universe, you have supernovae going off, and in the case of the chameleons, you have these domain walls in there. That means that when I'm applying, if I'm plotting, for instance, the gamma parameter here in log scale, okay, as a function of the radius from the Milky Way, so the solar system, so this is the Milky Way, it's about 10 kiloparsec in scale, here, 10 kiloparsec. The solar system is about in an arm of about 8 kiloparsec to the center of the Milky Way. Okay, so if I use, for instance, the symmetron model, my gamma ppn parameter is proportional to the phi square, the gravitational potential, etc. I can plot what is the profile of my gamma parameter as a function of my scalar field. So in the center of the Milky Way, if I assume there's Sagittarius A star, the black hole, the supermassive black hole, then my chameleon is completely screened near the black hole. Yes, but as I go to the outskirts a little bit to 8 kiloparsecs, so that's my solar system, my scalar field already is not zero because the density changed a little bit, so my scalar field gains some profile. And if I go to the outskirts of the galaxy, that will the scalar field gains even more profile. So the gamma, the ppn parameter, becomes different from 1 as I go to the outskirts of my galaxy because the density becomes lower, so there's less screening. Yeah? So when I assume the quasi-static approximation, I calculate this profile of my scalar field of gamma, and my Cassini bound says, in the solar system, I need to be below 10 to the minus 5. Yeah? That's what the Cassini probe tells me in my solar system when I do the experiment. So I need to go below this 10 to the minus 5, and when I look here, I'm safe because it's about 10 to the minus 8. So gamma for the symmetron is 10 to the minus 8. So I'm all happy and say, well, with the symmetron, I can do modified gravity, and it's safe for the Cassini probe bound. The problem is that we have domain walls, we have supernovae, so these domain walls are going to be waves coming from the outside of the galaxy, and we did some simulations, which will spoil this profile. And when you see this profile, this is what happened. I can do it again. So this is with the quasi-static approximation. So when I have a wave coming from the outside, for instance, for the case of the symmetron, is a domain wall collapsing. For the case of the chameleon, is similar. It's a supernova. We will see that then the profile of my gamma ppn parameter, which was 10 to the minus 8, now is 10 to the minus 2. And that's ruled out by the Cassini probe. Okay? So screening mechanisms, they can be a very good way of hiding your extra scalar degrees of freedom or vector degrees of freedom in your modified theory of gravity. But when you do the calculations, you should also take into account phenomena that might happen outside the solar system and outside even outside our galaxy, because these waves, the quasi-static approximation that we use to calculate the Weinstein radius, the symmetron or the chameleon or the camouflage, etc., they might not be enough. Now, what is interesting is that we can get a smoking gun for our screening mechanism as well, because these oscillations that I'm showing you here on the ppn parameter, they can be in fact a signature, because if there's a supernovae going off, we can wait to see how long this scalar field takes to propagate through our galaxy, through our solar system, to see if our ppn goes up to 10 to the minus 2 with the Cassini. And then this wave goes by, so that means my Cassini gamma will come down again. And if there's another supernovae, that will go up again because my wave comes down. So we have these oscillations, and this is a smoking gun for the existence of screening mechanisms. If we see oscillations in the gamma parameter, we did the calculations to see what is the frequency of these oscillations, how could I? And it's about 1 million years. So we have to keep mankind alive for 1 million years and to keep a Cassini probe there for 1 million years to see the next oscillation in there. So might not be the most realistic thing, but okay. But I think I'll finish here. Maybe I'll just leave you with my final slide. So my final slide, sorry, I didn't have time to cover the whole thing, but my idea is to probe screened modified theories of gravity. So I think if you have a theory of modified gravity, you need to screen it somehow. Otherwise, it's ruled out by laboratory experiments. So laboratory experiments, they are really important because it's the most controlled experiment that you can do. Yes, you control all your systematics. You know you're doing this with, with neutrons or with the standard model fields that you understand the physics very well. And they are really, really constrained, the solar system and laboratory. The problem is that you are constrained deviations of gravity at very small time scales. It's just usually a couple of years at maximum. And you're also probing gravity at small scales, at astronomical unit. So who says so Newtonian gravity is valid on Earth, but it's not valid on the solar system. So maybe general relativity is valid on the solar system, but it's not valid at galaxy scales. We don't know. So laboratory experiments have this limitation there. Astrophysical scales, these are really important, and for me, the most promising ways of probing screening mechanisms. The problem is that the physics is very complicated. It's nonlinear gravity, and we have lots of baryonic effects. And that's very complicated. It's very complicated to disentangle nonlinear structure formation and with all the baryonic physics in there. But, they fit the range of the phi force is megaparsec. Yeah, so that's the galaxy cluster. Check modified gravity along the history of the universe. We can check with Big Bang nucleosynthesis bounds, the cosmic microwave background radiation. The mathematics is very simple. It's just linear perturbation theory. So it's quite simple mathematics, very easy to integrate. Although, one of the problems is that there is this dark matter, dark energy. So if we find some theoretical model, some smoking gun of a modification gravity, how do we know it's modification of gravity, or is just a dark matter candidate, or it is just a dark energy candidate? So that's very difficult in that respect in there. So I think if we are looking for modified gravity, we need to look at all fronts, and try to see signatures in all fronts. Okay, thank you, everyone. Thank you.
Any questions?
Hello. So, sorry, I didn't listen for the beginning, but when I review about symmetron model, they said that they have problem to find a cosmological solution because of shape of potential. And I remember that they have to add cosmological constant in the end. So this situation is better now or not?
No, it's not much better now. No. So any of these theories of modified gravity, the whole motivation would be to be alternatives to the cosmological constant. So alternatives to dark energy. In practice, the cosmological constant problem is hidden inside the theory. So we always have to tune the potential, we always have to tune the properties of the scalar field, the shape of the f of r, to put the cosmological constant there. So none of them solve the cosmological constant problem, basically. So now you wonder, why shall we make our life more complicated, and just not use the cosmological constant? And that's a very good question. Up to, I think, nowadays, the cosmological constant with the Hubble tension, which is now on 6 sigma, that's something that lambda CDM cannot solve, the Hubble tension. We have also indications from the CMB photons, which get hotter as they go through gravitational wells. It should be the opposite. So lambda CDM also cannot explain it. So now we start to see some evidence that maybe lambda CDM is a minimalistic theory to explain the observations, but might be wrong. So you do not, even if it's less parameters, you do not want to use it. But it's true that we haven't solved the cosmological constant problem in this series of modified gravity. Other f of r or symmetron or chameleons or DGPs, absolutely, still a problem. Yeah.
Thank you.
All right.
Yes. My question is about the symmetron. So it's a single field. So I was just wondering that in one part of the universe, why it settled down in one atom and another one in another minimum? How? Because it's a single field throughout the universe.
Why it's not the same? Oh.
Yes.
Okay. So it's not the same. So it's not the same because the symmetron has a Compton wavelength, which is about 1 megaparsec, and that gives you basically the length of causality for the symmetron. So above this Compton wavelength, the symmetron can either fall in one minima of the potential or the other. Because so the symmetron has to choose, basically, yes, and we have two choices. So it either goes into the left-hand side or to the right-hand side.
That is my question. Like it's a single field, so why you choose in a particular region to go to the green one and in another region to go to the yellow one?
Yeah, well, that's just a causality issue. It's just like because the symmetron has a Compton wavelength, and that gives you more or less a causal region for the symmetron. So it might happen that the whole universe has the symmetron in one place. But statistically, it's more likely that in some parts of the universe go to one, and other parts of the universe go to another. But these parts of the universe, they need to be somehow causally disconnected, let's say. Yes, because the universe expands, so not the whole universe is causally connected. Yes, the speed of light is finite. So we have some regions of the universe which are not in causally contact with other ones. So in those regions, the symmetron might go to the left, and in other regions, the symmetron might go to the right. So it's related to causality, in fact. Yeah. If I was clear, okay.
Hello. Yeah, I think from this slide, I think if like the scalar field become like the complex scalar field, the -1 and +1 can be connected, like U1 theory, kind of, right?
Yes. So if the scalar field is complex here, then you get the U1 symmetry, and instead of domain walls, you have cosmic strings, which is another topological defect.
Oh, okay. Yeah.
Yes. So you still have topological defects, yeah. But now they are cosmic strings; they're not domain walls. Yes.
Yeah. Okay.
For
And
complex scalar fields, yes.
maybe I have another stupid question. So what is smoking gun mean?
Smoking gun just means an observation that might indicate that you have found something. It's just like, I don't know, maybe that's a cowboy western thing, Someone shoots, and you look at people's guns, oh, that one is smoking going out, so it might be you are the one who shot. So it's sorry. It's just,
Is that with evidence? Some evidence. Evidence.
Yes, it's like evidence. Yes, yes. Smoking gun would be evidence for that. Yeah, I should use a more scientific language.
That is good.
Yeah.
I understand.
Yes. Yes.
Other questions? No more questions. Please big thanks again for the whole nice lecture. Okay, we have tutorial class, and then from it, I will see David talk. He takes some equations, the slide, and somehow you don't know get that equations that in the tutorial. For example, I show you can make it first, and then show you how to get that equations. Okay, this is a tutorial class. Okay, and then I think we have inner box out there. Get it? Maybe I was on after dinner. So usually some people act like a kid. If you want tutorial class, eating before the time, after you have dinner, and then you come back maybe 30 minutes or 1 hour, I can make a tutorial earlier so that we can get earlier and enjoy this other classics.
In that case, I
So-
think you are happy, right?
So you mean that they take a lunch, a dinner box, and then but they still start tutorial immediately, right?
Maybe just
Or eating.
because we have 2 hours for dinner.
Yeah, it may be too long, so you can.
just you can get only 30 minutes. Finish right.
Then,
Usually.
then you can set that we can start at 5:30, something like that, and yeah, finish 7:30, something like that, and yeah, let them enjoy the life. Yeah.
Yeah. If you all prefer like that, it's okay. I can make. Do you want to make a tutorial earlier? Okay, small stuff.
Yeah, I think it's better. Yeah.
Okay, in that case, okay. We can make maybe about 5:30.
Yeah, 5:30. Yeah.
5:30. Oh, maybe another announcement. Since tomorrow you have to, some of you have to get back to your home, right? So that you have to check out the dorm. And the way you check out is just you turn the key into the small box. What that is. Yeah. The one you take the key. Yeah. That's that place. Okay. You turn the key at that place at the same time.
You mean like at the guard, the security? Yeah, security. Yeah. Okay.
Okay. That's all.